Imagine standing at the edge of an infinite abyss, a place where every star is a solitary candle in the darkness, and every galaxy is a distant beacon in an endless, silent ocean. Do you feel it? That profound and paradoxical sensation of utter insignificance and, at the same time, of a wonderful, ineffable connection to something so vast that it transcends all human understanding. The universe, that endless, mysterious space, holds more questions than answers, more mysteries than certainties, and every day, as we gaze up at the night sky, we are witnesses to a light that has traveled for millions, even billions, of years to reach our eyes, carrying with it messages from a time so ancient that our own planet had not yet been born. But what if we told you that what we see, this glorious tapestry of light and darkness, is just a fraction of the truth? What if the underlying reality of the universe is so strange, so powerful, and so overwhelming that it would change everything we think we know about our own existence? In the far, silent reaches of the cosmos, there lurk objects so dense and so gravitationally powerful that not even light itself, the fastest thing in the universe, can escape their grasp. These are the black holes, the dark, enigmatic giants of our universe. For decades, they were considered only theoretical curiosities, strange and unsettling solutions to Albert Einstein's elegant mathematical equations of general relativity. No one could truly imagine that such a monster, a true tear in the very fabric of space-time, could actually exist. But we now know they are real, and they are everywhere. When a star many times more massive than our sun exhausts the nuclear fuel in its core, the outward pressure that has held it up against its own immense gravity for millions or billions of years suddenly vanishes. A cataclysmic, gravitational collapse ensues. The entire mass of the star begins to fall inward upon itself, crushing matter into a state of unimaginable density. A singularity is created, a point of theoretically infinite density and zero volume, a place where our current laws of physics, our most fundamental understanding of the world, cease to make sense, and where space and time are bent and twisted into shapes that defy our three-dimensional intuition. Around this singularity lies a boundary, a one-way membrane called the event horizon. It is the ultimate point of no return. Anything that crosses this boundary, a planet, a star, a photon of light, a piece of information, will never come back. It is as if a part of the universe has been surgically and irrevocably removed, its contents forever hidden from our view. The physics of what happens to an object as it approaches a black hole is the stuff of cosmic horror. You would experience a phenomenon that astronomers have playfully, yet chillingly, dubbed spaghettification. The gravitational force of the black hole is so incredibly strong, and it changes so rapidly with distance, that the pull on your feet would be exponentially stronger than the pull on your head. Your body would be stretched, elongated, and pulled into a thin, single strand of atoms, like a noodle of spaghetti, before being torn apart and consumed by the singularity. For decades, black holes remained an invisible menace, their presence inferred only through their gravitational effects on nearby stars. But in April of 2019, humanity, for the first time, saw the shadow of a black hole. A huge international collaboration of scientists connected 8 radio telescopes across the globe, from Hawaii to the South Pole, creating a virtual telescope at the size of the Earth itself. This monumental project, the Event Horizon Telescope, captured an image of the supermassive black hole at the center of the galaxy M87, 55 million light-years away. What we saw was not the black hole itself, for it is by definition unseeable. What we saw was its silhouette, the light from the superheated gas and dust that was swirling around it in a final, fiery death spiral, just moments before crossing the event horizon. It was a bright, shimmering ring of light surrounding a perfect circle of darkness, the abyss itself. Humanity had finally looked into the face of one of the most terrifying and fundamental objects in the universe. And while supermassive black holes lie safely in the centers of distant galaxies, there is growing evidence that smaller, stellar mass black holes, the remnants of dead stars, may be far more common than we thought. Some of these could be rogue black holes, ejected from their birthplaces and now wandering silently and invisibly through the dark spaces between the stars. The idea of such a dark, unseen predator drifting through the galaxy is a true astronomer's nightmare. If such a rogue black hole were to pass through our solar system, we would not see it coming. We would only feel its immense gravitational presence as it began to warp the familiar, stable orbits of the planets, potentially flinging Earth into the cold depths of interstellar space, or sending it on a collision course with another world. The relationship between black holes and the fundamental nature of realities delves even deeper. Beyond the event horizon, the roles of space and time themselves are thought to switch. Time, for an object falling in, becomes a spatial direction, an inexorable path leading towards the singularity. Space, in turn, becomes time-like, a fleeting, transient dimension. This is a reality so alien to our own that our language and our intuition fail us. It is a realm where the two great pillars of modern physics, Einstein's general theory of relativity and quantum mechanics, come into direct and violent conflict. Relativity describes a smooth, deterministic space-time, while quantum mechanics describes a probabilistic, uncertain world. At the singularity of a black hole, where an immense mass is crushed into an infinitesimally small space, both theories must apply, and yet they give contradictory, nonsensical answers. This is the great unresolved challenge of modern physics, the quest for a theory of quantum gravity that can unite these two warring narratives. Some of the most brilliant minds in physics have dedicated their lives to this quest, and their speculative theories offer tantalizing, if unproven, glimpses of what might lie beyond the veil of the event horizon. Some theories suggest that the singularity is not a point of infinite density, but a fuzzball of vibrating strings from string theory, or a bounce where the collapsing matter is repelled by quantum gravitational forces and explodes into a new, baby universe. Others propose the existence of wormholes, theoretical tunnels in space-time that could connect the inside of a black hole to another point in our universe, or even to a parallel universe entirely. These are ideas that are on the very frontier of our scientific imagination. But the mysteries of black holes are not just theoretical. The discovery by Stephen Hawking that black holes are not entirely black, that they slowly evaporate over immense timescales by emitting a faint thermal radiation, has changed our understanding of these objects forever. This Hawking radiation, born from the quantum fluctuations of the vacuum near the event horizon, implies that black holes are not eternal prisons, but are dynamic objects with a finite lifespan. It also leads to the profound information paradox, the question of what happens to the information of the things that fall into a black hole. Is it truly destroyed, in violation of the fundamental principles of quantum mechanics, or is it somehow preserved and released in the outgoing radiation? The resolution of this paradox is thought to be a key step towards a theory of quantum gravity, and the diversity of black holes in the universe is staggering. We have found primordial black holes, hypothetical objects that could have formed from the dense fluctuations of the early universe, and which could even be a candidate for dark matter. We have found stellar mass black holes, the remnants of massive stars, and intermediate mass black holes, the missing link between the stellar and supermassive varieties. And at the heart of almost every large galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational behemoth with a mass of millions or even billions of suns. Our own central black hole, Sagittarius A, has a mass of about 4 million suns. These galactic giants are not just passive objects. They are active engines that play a crucial role in the evolution of their host galaxies, their powerful jets and radiation regulating the rate of star formation and shaping the very structure of the cosmos on the largest scales. It is a profound and beautiful irony that these objects of ultimate destruction, these gravitational abysses from which nothing can escape, are also, in a deep and fundamental sense, crucial architects of cosmic creation. They are the dark, mysterious hearts around which the luminous beauty of the galaxies revolves. When we look up at the night sky, we see a universe of light, a cosmos filled with the familiar matter of stars, planets, and galaxies. But this is a profound and humbling illusion. All of this visible, baryonic matter Everything that we have ever seen or touched, everything that makes up our bodies, our planet, and our sun, constitutes a mere 5% of the total mass and energy content of the universe. Another 27% is composed of a mysterious, invisible substance that we have come to call dark matter. It is the silent, unseen majority, an invisible giant that permeates the cosmos, its gravitational influence shaping the destinies of galaxies and the very architecture of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, or any other form of electromagnetic radiation. It is, for all intents and purposes, completely transparent, passing through us and our planet as if we were not even there. The only way we know of its existence is through the powerful and undeniable pull of its gravity. The first hints of this invisible substance came in the 1930s, when the brilliant and irascible Swiss-American astronomer Fritz Zwicky was studying the motions of galaxies within the Coma cluster. He noticed something deeply puzzling. The individual galaxies were moving at incredibly high speeds, so fast that the visible mass of the cluster, the combined mass of all its stars and gas, was not nearly enough to gravitationally bind them together. The cluster should have flown apart billions of years ago. To explain this discrepancy, Zwicky proposed the existence of a vast amount of unseen, dark matter, or Dunkelmaterie in his native German, providing the extra gravitational glue that was holding the cluster together. For decades, his observation was largely dismissed by the astronomical community as a strange anomaly. But in the 1970s, the pioneering work of astronomer Vera Rubin and her colleague Kent Ford provided a new and powerful line of evidence that could no longer be ignored. They were studying the rotation curves of spiral galaxies, measuring the orbital speeds of stars at different distances from the galactic center. According to Newton's laws of gravity, the stars in the outer regions of a galaxy, where most of the visible matter is concentrated towards the center, should be moving much more slowly than the stars closer in. But this is not what Rubin and Ford found. They discovered that the outer stars were orbiting at almost the same speed as the inner stars, as if the galaxy were a solid, rotating disk. This was a stunning and revolutionary result. The only way to explain these flat rotation curves was to posit that each galaxy is embedded in a vast, spherical halo of invisible dark matter, a halo whose mass extends far beyond the visible edge of the galaxy and provides the extra gravitational pull needed to keep the fast-moving outer stars in their orbits. Since then, the evidence for dark matter has become overwhelming. We see its effects in the gravitational lensing of distant light, where the gravity of massive galaxy clusters, far greater than their visible mass could account for, bends and distorts the light from objects behind them, acting as a cosmic magnifying glass. We see it in the temperature distribution of the hot gas and galaxy clusters, and we see it in the very structure of the universe on the largest scales, the cosmic web of filaments and voids, which our computer simulations show could not have formed without the gravitational scaffolding of dark matter in the early universe. Our own Milky Way is no exception. It is thought to be surrounded by a massive dark matter halo that is perhaps 10 times more massive than all the visible stars, gas, and dust in the galaxy combined. Without this invisible cocoon, our beautiful spiral galaxy would not exist in the form we know it today. But what, precisely, is this dark matter? This remains one of the greatest and most profound unsolved mysteries in all of science. The leading hypothesis is that it is composed of a new, as yet undiscovered type of elementary particle, a particle that is not part of the standard model of particle physics that so successfully describes all the known particles and forces. These hypothetical particles would have been created in the hot, dense conditions of the early universe, and they would interact with normal matter only through the force of gravity and, perhaps, the weak nuclear force. This is why they are so difficult to detect. The most popular class of candidates for these particles are WIMPs, which stands for weakly interacting massive particles. These would be relatively heavy particles, perhaps 100 to 1,000 times the mass of a proton. Another leading candidate is the axion, a much lighter hypothetical particle that was originally proposed to solve a different problem in particle physics, the strong CP problem. The search for these elusive dark matter particles is a major international scientific endeavor, a three-pronged attack that is pushing the limits of our technology. In deep underground laboratories, shielded from the constant rain of cosmic rays, experiments with incredibly sensitive detectors, made of materials like liquid xenon or germanium crystals, are patiently waiting to catch the rare, fleeting signal of a WIMP bouncing off an atomic nucleus. So far, after decades of searching, these direct detection experiments have come up empty-handed. At particle accelerators like the Large Hadron Collider at CERN, physicists are trying to create dark matter particles directly by smashing protons together at nearly the speed of light and looking for missing energy and momentum in the debris of the collision, a sign that some invisible, massive particles have been produced and have escaped the detector. This search, too, has so far been unsuccessful. The third prong is indirect detection. Space-based telescopes, like the Fermi Gamma Ray Space Telescope, are looking for the byproducts of dark matter annihilation. If two dark matter particles were to collide and annihilate each other in a dense region of the cosmos, like the center of our galaxy, they could produce a shower of familiar particles, including a telltale signal of high-energy gamma rays. There have been some intriguing, but not yet definitive, hints of such a signal from the galactic center. The persistent failure of these searches has led some physicists to consider more exotic possibilities. Perhaps dark matter is not a single particle, but a whole dark sector of particles, with its own new forces. Perhaps it is made of primordial black holes, microscopic black holes that could have formed from the dense quantum fluctuations of the early universe. Or perhaps, as a minority of physicists argue, dark matter does not exist at all, and the strange gravitational effects we observe are a sign that our understanding of gravity itself is incomplete. These modified gravity theories, like Mund-modified Newtonian dynamics, propose that the law of gravity changes on galactic scales. While these theories can explain the rotation curves of galaxies quite well, they struggle to account for the full range of cosmological observations, such as the behavior of colliding galaxy clusters. The mystery of dark matter is a profound and humbling one. It tells us that we are blind to 85% of the matter in our own universe. We are strangers in our own cosmic home, surrounded by an invisible, unknown substance whose nature remains a deep and tantalizing puzzle. And while dark matter appears to be a benign, gravitational glue that holds our universe together, the thought that our reality is governed by an invisible, omnipresent, and utterly alien form of matter is, in its own way, a deeply unsettling and terrifying thought. The cosmic inventory of the unknown is not limited to dark matter. As we have seen, all the matter in the universe, both the visible matter that we know and the dark matter that we don't, makes up only about a third of the total energy density of the cosmos. The remaining two-thirds, a staggering 68% of the universe, is composed of an even more mysterious and enigmatic entity, dark energy. If dark matter is the invisible gravitational glue that holds the universe together, dark energy is the invisible, repulsive force that is tearing it apart, and its discovery, at the very end of the 20th century, represents one of the most profound and revolutionary shifts in our understanding of the cosmos since the time of Einstein. For most of the 20th century, the prevailing cosmological model was one of a universe whose expansion was slowing down, a universe where the mutual gravitational attraction of all the matter within it was acting as a cosmic brake. The only question was whether there was enough matter to eventually halt the expansion and cause the universe to recollapse in a big crunch, or whether the expansion would continue forever, but at an ever-decreasing rate. Then, in 1998, two independent teams of astronomers, using distant type Ia supernovae as standard candles to measure the expansion history of the universe, made a discovery that was so shocking, so utterly unexpected, that it shook the foundations of cosmology. They found that the distant supernovae were dimmer and therefore further away than they should have been in a decelerating universe. The expansion of the universe is not slowing down, it is accelerating. This groundbreaking discovery, which earned its leaders the 2011 Nobel Prize in Physics, implied the existence of a new, previously unknown component of the universe, a component with a strange and powerful property, a strong negative pressure that acts as a form of cosmic anti-gravity, pushing space-time apart. This is what we call dark energy. But what is it? This remains one of the greatest unsolved mysteries in all of science. The simplest, and currently most favored, explanation is that dark energy is the cosmological constant, a concept first introduced by Albert Einstein into his equations of general relativity in 1917. Einstein had added this term to his equations to counteract the attractive force of gravity and allow for a static, unchanging universe, which was the prevailing view at the time. When Edwin Hubble later discovered that the universe was, in fact, expanding, Einstein famously called the cosmological constant his biggest blunder. In a beautiful twist of historical irony, modern cosmology has resurrected Einstein's blunder and made it the centerpiece of our standard cosmological model. A cosmological constant represents an intrinsic energy of space-time itself, an energy of the quantum vacuum, and it has a very strange property. As the universe expands, the density of matter and radiation decreases as they are spread out over a larger volume, but the density of vacuum energy remains constant. This means that as the universe gets bigger, the total amount of dark energy increases. It is as if new energy is being continuously created from the expanding space itself. In the early universe, when the density of matter was very high, the effects of dark energy were negligible, but as the universe expanded and thinned out, dark energy gradually became the dominant component. It took over from gravity as the primary driver of cosmic evolution about 5 billion years ago, and it has been accelerating the expansion ever since. The problem, as we have discussed, is the vacuum catastrophe. The theoretical value of this vacuum energy, as calculated from quantum field theory, is an absurd 120 orders of magnitude larger than the observed value of dark energy. This colossal discrepancy has led many physicists to believe that the simple identification of dark energy with the cosmological constant must be wrong. This has spawned a host of alternative theories. Perhaps dark energy is not a constant, but a dynamic entity, a new, evolving scalar field that has been dubbed quintessence. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps, more radically, our understanding of gravity itself is incomplete. Maybe general relativity needs to be modified on cosmological scales, and the accelerated expansion is not caused by a new form of energy, but by a change in the law of gravity itself. The nature of dark energy is a question of profound and existential importance. It will determine the ultimate fate of our cosmos. If dark energy is a cosmological constant, then the universe is destined for a big freeze, an endless, accelerating expansion into a cold, dark, and empty future. If dark energy is a phantom energy that grows stronger over time, then the universe could end in a big rip, where the fabric of space-time itself is torn asunder. The discovery of dark energy is a humbling one. It tells us that not only are we blind to the majority of the matter in the universe, but we are also ignorant of the dominant force that is shaping its destiny. We live in a cosmos that is governed by two great dark mysteries, a cosmic battle between the attractive force of dark matter and the repulsive force of dark energy, a battle whose ultimate outcome will decide the fate of all that is. The nature of time, a concept so familiar and yet so deeply mysterious, has been revolutionized by the discoveries of modern physics. For most of human history, time was conceived as an absolute, universal, and unchanging river, flowing at the same rate for everyone and everything in the cosmos. This was the time of Isaac Newton, a fixed and eternal backdrop against which the clockwork motions of the universe played out. But in the early 20th century, a young patent clerk named Albert Einstein shattered this timeless illusion forever. His special theory of relativity, published in 1905, revealed that time is not absolute, but relative. It is a dynamic and flexible entity, inextricably interwoven with space into a single-soul four-dimensional continuum called space-time. And the rate at which time passes depends on your motion through this space-time. The faster you move through space, the slower you move through time, relative to a stationary observer. This phenomenon, known as time dilation, is not a trick of perception, it is a real physical effect. An atomic clock on a fast-moving jet will tick slightly slower than an identical clock on the ground. An astronaut on a long journey at near-light speed would return to Earth to find that they have aged less than their twin sibling who stayed at home. This means that travel to the future is, in a sense, a physical possibility. If you were to embark on a round trip to a nearby star at a speed very close to the speed of light, you might experience only a few years of time, but when you return to Earth, you would find that centuries, or even millennia, had passed. You would have effectively traveled into the future of the Earth. But Einstein's revolution did not stop there. His general theory of relativity, published in 1915, revealed an even deeper connection between space-time and the contents of the universe. Gravity, he showed, is not a force that acts in space. It is a manifestation of the curvature of space-time by mass and energy. Massive objects warp the geometry of space-time around them, and other objects simply follow the straightest possible path, a geodesic, through this curved space-time. And this curvature affects not just space, but time as well. Time runs more slowly in a stronger gravitational field. This gravitational time dilation is a real and measurable effect. The atomic clocks on our GPS satellites, which are in a weaker gravitational field than we are on the surface of the Earth, run slightly faster than clocks on the ground. If this effect were not constantly corrected for, the entire GPS system would accumulate errors of several kilometers per day and would be completely useless. The effects of gravitational time dilation become truly extreme near a very massive and compact object, like a black hole. At the event horizon of a black hole, the curvature of space-time is so intense that time, from the perspective of a distant observer, would appear to grind to a complete halt. A friend falling into a black hole would seem to be frozen in time at the event horizon, their image getting ever redder and dimmer, but never actually crossing the point of no return. For the friend themselves, however, time would continue to pass normally as they fell towards the central singularity. This relativity of time, its dependence on motion and gravity, is a profound and counterintuitive feature of our universe. But what about travel to the past? While Einstein's equations do not explicitly forbid it, they do suggest that it would require some very exotic and likely impossible physics. It would necessitate the existence of closed time-like curves, paths through space-time that would allow you to return to your own past. These could potentially be created by structures like wormholes, theoretical tunnels connecting distant points in space-time, or by infinitely long, rapidly rotating cylinders. But most physicists, including Stephen Hawking, believe that the laws of nature have a built-in chronology protection conjecture, a mechanism that prevents the formation of these time loops and the paradoxes, like the famous grandfather paradox, that they would create. The quantum world adds another layer of strangeness to our understanding of time. As we have seen, the arrow of time seems to be rooted in the second law of thermodynamics. But at the fundamental quantum level, the laws of physics are largely time-symmetric. Some speculative interpretations of quantum mechanics even suggest that the past, present, and future may all exist simultaneously in a block universe, and that our sense of a flowing time is an illusion of our consciousness. The nature of time remains one of the deepest and most challenging mysteries in all of science. It is a concept that lies at the very intersection of physics, philosophy, and our own subjective experience. And the discoveries of the last century have shown us that our intuitive, common-sense understanding of time as a simple linear flow is just a small, local approximation of a much richer, stranger, and more wonderfully complex reality. The idea that our universe might not be the only one, that it could be part of a vast, perhaps infinite, multiverse of parallel realities, is a concept that pushes the boundaries of our scientific imagination. It is an idea that has been explored in countless works of science fiction, but in recent decades, it has also become a serious and compelling subject of investigation in theoretical physics and cosmology. The multiverse is not a single, monolithic theory, but rather a spectrum of different models, each arising from different physical principles and each with its own, unique set of implications. The first, and perhaps most straightforward, type of multiverse is the level 1, or quilted multiverse. This arises from the simple, and very likely true, assumption that space is infinite. If our universe extends forever in all directions, then in that infinite volume, every possible configuration of matter and energy that is allowed by the laws of physics must, by statistical necessity, occur not just once, but an infinite number of times. This means that somewhere out there, far, far beyond our cosmic horizon, there is another region of space, a Hubble volume, that is identical to our own. There is another galaxy, another solar system, another Earth, and another you, an identical copy who is, at this very moment, reading these very words. And there are an infinite number of such copies, as well as an infinite number of near copies, where every possible variation of your life is being played out. This is a staggering and deeply unsettling thought, one that challenges our most basic sense of individuality and uniqueness. A second, and more physically motivated, type of multiverse is the level 2 or inflationary multiverse. As we have seen, the theory of eternal cosmic inflation suggests that our universe is just one bubble that nucleated from an eternally expanding meta-universe. Other bubbles are constantly being formed, and each one could, in principle, have different physical laws, constants, and even different numbers of dimensions. This creates a vast, and perhaps infinitely diverse, landscape of different physical realities. This is a powerful idea, as it provides a natural, scientific framework for addressing the fine-tuning problem. The reason our universe has life-friendly laws is simply because we are living in one of the rare bubbles where that is the case. A third, and perhaps the most bizarre, type of multiverse is the level 3, or many worlds multiverse of quantum mechanics. As we discussed, this interpretation, first proposed by Hugh Everett, posits that the wave function never collapses. Instead, every quantum event with multiple possible outcomes causes the universe to split into multiple, parallel branches, one for each outcome. This creates a constantly branching and unimaginably vast tree of parallel realities. Every time a radioactive atom has a chance to decay, the universe splits. In one branch, it decays, in the other, it does not. In one branch, Schrödinger's cat lives, in the other, it dies. Every choice you have ever made, every coin you have ever flipped, has created a new set of parallel universes, where every possible outcome was realized. This is a vision of reality that is almost impossible to fully grasp. A reality where all possibilities are not just potential, but are all, in their own branch of the multiverse, actual. Finally, there is the most abstract and philosophical of all multiverses, the level 4, or mathematical multiverse, proposed by Max Tegmark. This is the hypothesis that all mathematically consistent structures have a physical existence. Our universe is just one such structure, and every other possible mathematical reality, from the simplest to the most complex, also exists as a separate universe. This is the ultimate expression of Platonism, the idea that the world of mathematical forms is the true fundamental reality. The multiverse, in all its forms, is a deeply speculative and controversial idea. Its primary weakness is that, by its very nature, it is untestable. We can never hope to travel to another bubble universe, or to communicate with a parallel branch of the quantum wave function. This has led many to argue that the multiverse is not science, but metaphysics. But its proponents argue that the theories from which it arises, like inflation and quantum mechanics, are themselves highly testable, and if they continue to be confirmed, we may have to take their bizarre and wonderful consequences seriously. Whether the multiverse is real or not, the very fact that it is a serious topic of discussion is a testament to the incredible power and reach of the human mind. It is a concept that forces us to confront the true and perhaps infinite scale of reality, to question our most cherished assumptions about our own place in the cosmos, and to embrace a vision of existence that is infinitely richer, stranger, and more magnificent than anything our ancestors could have ever dreamed. Our perception of the world is fundamentally shaped by our three-dimensional intuition. We live in a world of length, width, and height, a world where we can move up and down, forward and backward, left and right, and we experience this three-dimensional space as it evolves and changes in a fourth dimension, the dimension of time. But is this familiar? Four-dimensional space-time the whole of reality? Or could it be just a small, visible slice of a much larger and much more complex, multidimensional cosmos? The idea of extra hidden dimensions of space is not a new one. It has been a recurring theme in mathematics and physics for over a century, but it has been given a new and powerful life in the context of modern string theory, one of the leading candidates for a unified theory of everything. String theory is a breathtakingly ambitious attempt to unite all the forces and particles of nature, including gravity, into a single, coherent mathematical framework. And it does so by proposing a radical new picture of the fundamental constituents of reality. In string theory, the elementary particles we see in our experiments, the electrons, the quarks, the photons are not point-like objects. They are, in fact, tiny, one-dimensional, vibrating strings of energy. And the different ways these strings can vibrate, the different notes they can play, correspond to the different particles we observe. An electron is a string vibrating in one pattern, a photon is a string vibrating in another, and, most importantly, one particular vibrational mode of a closed, loop-like string corresponds to the graviton, the hypothetical quantum particle of gravity. In this way, string theory naturally and elegantly incorporates gravity into a quantum framework, something that has been a major stumbling block for theoretical physics for decades. But this beautiful, unified picture comes at a price. The mathematical consistency of the theory, the requirement that it be free of paradoxes and infinities, only works if spacetime has more than the four dimensions we are familiar with. The most common versions of string theory require a total of 10 or 11 spacetime dimensions. So, where are these extra 6 or 7 spatial dimensions? The idea is that they are compactified, curled up into a tiny, complex geometrical shape at every single point in our familiar, three-dimensional space. Imagine an ant crawling on a long, thin garden hose. From a great distance, the hose looks like a simple, one-dimensional line. But for the ant, who is living on its surface, there is a second circular dimension that it can crawl around. In the same way, the extra dimensions of string theory are thought to be curled up on a scale so incredibly small, the Planck length, about 10 to the power of minus 35 meters, that they are completely invisible to us and our current experiments. The precise shape and size of these extra, compactified dimensions, the geometry of what is known as a Calabi-Yau space, is not just a mathematical detail, it is the key to everything. It is the geometry of this hidden, inner space that determines which string vibrations are possible, and therefore, what the spectrum of fundamental particles and the values of the fundamental constants of our universe will be. The laws of physics are, in this sense, a consequence of the geometry of these unseen dimensions. This idea has led to the concept of brain cosmology, where our entire four-dimensional universe is a brain, short for membrane, a subspace floating in a higher dimensional bulk. The particles and forces of the standard model are confined to our brain, like characters in a two-dimensional cartoon, while gravity, the geometry of space-time itself, is free to propagate in the extra dimensions. This could explain why gravity is so much weaker than the other forces. Its influence is being leaked into the bulk. This scenario also opens up the possibility of a parallel universe on another brain, separated from us by a tiny distance in a hidden dimension. The Big Bang could have been the result of a collision between our brain and another. While these ideas are highly speculative and far from being experimentally proven, they are not just mathematical games. They are the logical consequences of taking our most promising unified theory seriously, and they offer a tantalizing, if mind-bending, vision of a reality that is far richer and more complex than our senses can perceive. The search for evidence of these extra dimensions is one of the great challenges of modern experimental physics, with scientists looking for subtle signatures at the Large Hadron Collider or in high-precision tests of gravity. Whether string theory and its extra dimensions are a true description of reality or not, the very idea has expanded our conception of what the universe could be. It is a powerful reminder that the familiar world of our three-dimensional experience may just be a shadow, a projection, of a much deeper, much stranger, and much more beautiful multidimensional reality. The phenomenon of quantum entanglement, the spooky action at a distance that so perplexed Albert Einstein, is perhaps the most profound and counterintuitive feature of the quantum world. It is a strange and intimate connection that can exist between two or more particles, a bond so deep that it seems to defy our classical notions of space, time, and causality. When two particles, such as a pair of photons, are created in a specific, entangled state, they are no longer independent entities. They are, in a very real sense, two parts of a single, unified quantum system, described by a single wave function. And this connection persists, instantaneously, no matter how far apart they are separated. If you take these two entangled photons and send one to a laboratory in New York and the other to a laboratory in Tokyo, they will remain linked. The strangeness becomes apparent when you make a measurement. According to quantum mechanics, a property of a particle, like its polarization, does not have a definite value until it is measured. It exists in a superposition of all possible polarizations. But for an entangled pair, the moment you measure the polarization of the photon in New York and find it to be, say, vertical, you instantly know, with 100% certainty, that if your colleague in Tokyo were to measure the polarization of their photon at the same time, they would find it to be horizontal. It is as if the measurement in New York has instantaneously collapsed the wave function of the entire entangled system, forcing the photon in Tokyo to choose the opposite state. This apparent faster-than-light communication deeply troubled Einstein, who believed it was a sign that quantum mechanics was an incomplete theory. He argued that there must be some hidden variables, some predetermined instructions that the particles carried with them from their creation, which dictated the outcomes of the measurements. For decades, this was a philosophical debate, but in the 1960s, the physicist John Bell devised a brilliant mathematical theorem that showed that it was possible to experimentally distinguish between the predictions of standard quantum mechanics and any theory based on such local hidden variables. In the decades since, numerous Bell test experiments have been performed with ever-increasing precision, and the results have been unambiguous. The universe is, indeed, as spooky as quantum mechanics predicts. Local hidden variable theories have been ruled out. The non-local connection of entanglement is a real, physical feature of our world. It is important to understand that this does not allow for faster-than-light communication. The outcome of the measurement on the first particle is fundamentally random. You cannot control whether you get a vertical or horizontal result, and therefore you cannot use this to send a deliberate, faster-than-light message. It is only when you later compare your results with your colleagues, a process that is still limited by the speed of light, that you can see the perfect and spooky correlation. But the underlying instantaneous connection is undeniably real. It tells us that our classical picture of a universe made up of separate, independent, and locally interacting objects is a profound illusion. At its most fundamental level, the universe is not a collection of things. It is a single, holistic, and indivisible web of interconnected relationships. This has deep philosophical and even spiritual implications. It is the physical basis for the ancient mystical intuition that all is one. The sense of separation we feel as individual beings is not the ultimate reality. We are all, in a very real, physical sense, entangled with each other, with our environment, and with the entire history of the cosmos. The atoms in our bodies are entangled with the atoms of the stars in which they were forged. The very act of observing a distant galaxy entangles us with its light. Quantum entanglement is the universe's most profound and beautiful secret. It is a secret that is not just a curiosity for physicists, but is also the foundation for a new generation of revolutionary technologies. It is the key to quantum computing, which promises to solve problems far beyond the reach of classical computers. It is the basis for quantum cryptography, which allows for the creation of unhackable communication channels. And it is the principle behind quantum teleportation, a process that allows for the transfer of a quantum state from one location to another. Quantum entanglement is a window into a deeper, more mysterious, and more interconnected reality. A reality where space is not a barrier, and where the universe, at its heart, is a single, beautiful, and profoundly unified whole. The story of the Big Bang is the story of our cosmic origins, the grand 14 billion year-long narrative of how our universe evolved from a state of almost unimaginable heat and density to the rich, complex, and beautiful cosmos we inhabit today. But it is a story that, in its standard form, begins at a moment of profound mystery, a moment where our current laws of physics break down the initial singularity. The Big Bang Theory is not a theory of the creation of the universe from nothing. It is a theory of the evolution of the universe from this initial, singular state. What came before, or what caused? This singularity remains one of the greatest unsolved questions in all of science. The story that the theory does tell begins at about 10 to the power of minus 43 seconds after the beginning of time, an epoch known as the Planck era. Before this time, the universe was so hot and dense that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were likely unified into a single, primordial superforce. To understand this era, we need a theory of quantum gravity, which we do not yet have. As the universe expanded and cooled, this superforce is thought to have frozen out, or separated, into the distinct forces we see today. The first to separate was gravity. Then, in a period of exponential expansion known as inflation, the strong nuclear force separated, releasing a tremendous amount of energy that drove the universe to expand by a colossal factor. After inflation, the universe was a hot, dense soup of fundamental particles, a quark-gluon plasma, as it continued to cool. At about 1 microsecond after the Big Bang, the quarks and gluons condensed to form the protons and neutrons that make up the nuclei of atoms. For the next 3 minutes, in a process known as Big Bang nucleosynthesis, the universe was a cosmic nuclear reactor. Protons and neutrons fused together to form the nuclei of the lightest elements, mostly hydrogen and helium, with trace amounts of lithium. The relative abundances of these light elements predicted by the theory match our astronomical observations with incredible precision, providing one of the strongest pieces of evidence for the Big Bang model. For the next 380,000 years, the universe remained a hot, dense, and opaque plasma. The temperature was too high for stable atoms to form, and the universe was filled with a sea of free electrons that constantly scattered the photons of light, creating a kind of cosmic fog. This was the dark age of the universe, not because there was no light, but because the light was trapped, unable to travel freely. Then, when the universe was about 380,000 years old, it had cooled to a temperature of about 3,000 Kelvin. At this point, the electrons were slow enough to be captured by the atomic nuclei, forming the first stable, neutral atoms of hydrogen and helium. This event is called recombination, and it was a pivotal moment in cosmic history. Suddenly, the cosmic fog lifted. The universe became transparent to light. The photons that had been trapped in the plasma were now free to stream across the cosmos, and they have been traveling ever since. We detect this ancient light today as the cosmic microwave background, CMB, a faint, uniform glow of microwave radiation that comes to us from all directions in the sky. The CMB is a baby picture of our universe, a snapshot of the moment it first became transparent. The tiny temperature fluctuations in this background radiation, about 1 part in 100,000, are the fossilized imprints of the primordial quantum fluctuations that were stretched to cosmic scales during inflation. And they are the seeds from which all the large-scale structures in the universe, the galaxies, the clusters, the cosmic web would later grow. After recombination, the universe entered a long period of darkness, as there were not yet any stars to light it up. But gravity was at work, slowly and patiently pulling the gas in the slightly denser regions together. Eventually, after a few 100 million years, the first stars ignited, bathing the universe in light for the first time and ending the cosmic dark ages. These first stars were massive, hot, and short-lived, and their explosive deaths in supernovae enriched the universe with the first heavy elements, the raw material for the next generation of stars and planets. Over the subsequent billions of years, this process of gravitational collapse and stellar evolution has continued, building up the rich and complex tapestry of the universe we see today. The Big Bang Theory is a magnificent scientific achievement, a story that is supported by a wealth of observational evidence. From the expansion of the universe and the cosmic microwave background to the abundance of the light elements. It is the story of our cosmic origins, a story of how, from a state of almost perfect simplicity, all the beauty and complexity of our world was born. The search for life beyond Earth. The quest to answer the age-old question, are we alone, is one of the most profound and exciting endeavors in all of science. For millennia, this question was the domain of philosophers and theologians. But in recent decades, it has become a true data-driven science, an interdisciplinary field known as astrobiology that brings together astronomers, biologists, chemists, and geologists. The search for extraterrestrial life begins with the search for habitable environments. And the key ingredient for life as we know it is liquid water. Water is a remarkable molecule, a universal solvent that can facilitate the complex chemical reactions that are the basis of biology. And so, the search for life is, in large part, a search for water. In our own solar system, there are several promising locations where liquid water may exist. Mars, our red neighbor, was once a much warmer and wetter world, with rivers, lakes, and perhaps even a shallow ocean. While its surface is now a cold, dry desert, there is strong evidence that liquid water still exists in underground aquifers. Future missions to Mars will drill beneath the surface, searching for signs of this hidden water, and for the fossilized, or perhaps even extant, microbial life that it might harbor. Even more exciting are the ocean worlds of the outer solar system. Jupiter's moon, Europa, and Saturn's moon, Enceladus, are both covered in a thick crust of ice. But beneath this ice, they are thought to hide vast, global oceans of liquid water, kept warm by the tidal forces of their giant parent planets. These subsurface oceans could be in contact with a rocky seafloor, where hydrothermal vents, similar to the black smokers on Earth's ocean floors, could provide a source of chemical energy and nutrients, creating a perfect environment for life to arise and thrive, completely independent of sunlight. Saturn's largest moon, Titan, offers an even more exotic possibility. It has a thick, nitrogen-rich atmosphere and a landscape of rivers, lakes, and seas. But on Titan, the liquid is not water. It is a mixture of methane and ethane. Could a form of weird life exist in this cryogenic environment? A life that uses methane as a solvent and has a completely different biochemistry from our own. But the search for life is not limited to our own solar system. In the last 3 decades, we have discovered thousands of exoplanets, planets orbiting other stars, and we have found that planets are incredibly common. There are likely more planets than stars in our galaxy. Many of these exoplanets are rocky, Earth-sized worlds, and a significant fraction of them orbit in the habitable zone of their star, the region where temperatures are just right for liquid water to exist on the surface. The next great challenge is to study the atmospheres of these distant worlds, searching for biosignatures, the chemical fingerprints of life. The James Webb Space Telescope is a powerful tool for this. By analyzing the starlight that filters through a planet's atmosphere, it can detect the presence of gases like oxygen, methane, and water vapor. A combination of these gases, particularly oxygen and methane, which are chemically unstable together, would be a strong indication of a living, breathing biosphere. The detection of life beyond Earth, even microbial life, would be a discovery of unparalleled significance. It would be a scientific revolution that would forever change our view of our place in the universe. It would tell us that life is not a unique and precious miracle of our own planet, but a common, and perhaps even inevitable, outcome of the laws of chemistry and physics playing out on a cosmic scale. But what about intelligent life? The search for extraterrestrial intelligence. SETI has been scanning the radio skies for decades, listening for the artificial signals of a distant, technological civilization. So far, the universe has been silent. This is the heart of the Fermi paradox. If the universe is so vast and so old, and if life is common, then where is everybody? The possible solutions to this paradox, from the rare Earth hypothesis to the Great Filter, are a sobering reminder of the immense challenges and potential dangers that may lie on the path from simple life to a long-lived interstellar civilization. The search for life beyond Earth is a journey into the unknown, A quest that is as much about understanding the universe as it is about understanding ourselves. It is a quest that is just beginning, and the answer, whatever it may be, will undoubtedly be one of the most profound and transformative discoveries in the entire history of the human species. The Fermi paradox, the stark and unsettling contradiction between the high probability of extraterrestrial life and the deafening silence of the cosmos, is a puzzle that has haunted scientists and thinkers for over half a century. It is a question that forces us to confront our deepest assumptions about the nature of life, of intelligence, and of our own future. The argument, first articulated by the physicist Enrico Fermi, is a simple but powerful one. Our galaxy contains hundreds of billions of stars, many of which are billions of years older than our Sun. A significant fraction of these stars likely have Earth-like planets in their habitable zones. If life arises on even a tiny fraction of these worlds, and if a fraction of that life evolves intelligence and technology, then the galaxy should be home to thousands, if not millions, of advanced civilizations. And even with technology not much more advanced than our own, a civilization could, in principle, colonize the entire galaxy in a cosmic blink of an eye, a few tens of millions of years. So, why do we see no evidence of their existence? No probes, no megastructures, no signals, just a profound and unnerving silence. The possible solutions to this paradox can be broadly grouped into three categories. The first is that we are, for some reason, alone, or at least the first. This is the rare Earth hypothesis, perhaps the specific set of conditions that allowed for the emergence of complex, intelligent life on Earth, a stable, long-lived star, a large moon to stabilize our axial tilt, plate tectonics, a protective magnetic field. The right chemical ingredients is so incredibly rare that we are, for all practical purposes, unique in our galaxy. This would make our existence a precious and fragile miracle, and it would place an immense responsibility on our shoulders as the sole custodians of consciousness in our corner of the cosmos. The second category of solutions is that they exist, but we have not found them yet. Perhaps interstellar travel is simply too difficult and too expensive for any civilization to undertake on a large scale. Perhaps they are hiding from us, following a zoo hypothesis or a policy of non-interference. Perhaps they communicate in ways that are far beyond our current technological capabilities, using neutrinos or gravitational waves or some form of physics we have not yet discovered. Or perhaps, in a more unsettling thought, they are so advanced, so alien, that we would not even recognize their presence if we saw it. We could be like an ant colony in the middle of a forest, completely unaware of the vast, complex, and intelligent human civilization that is building a superhighway right next to it. The third, and most terrifying, category of solutions is that they existed, but they are now all dead. This is the idea of the Great Filter, the hypothesis that there is some evolutionary or technological hurdle that is so difficult to overcome that it prevents almost all civilizations from reaching a long-lived interstellar stage. The chilling question is, where does this filter lie in relation to us? Is it in our past, or is it in our future? If the filter is behind us, then we are the lucky ones. We have passed the great improbable test, perhaps the origin of life itself, or the leap to multicellularity, or the emergence of human-level intelligence, was the Great Filter. This would make us a rare and precious exception. But if the Great Filter is still ahead of us, then the silence of the galaxy is a cosmic graveyard, a chilling and ominous warning. It would mean that countless civilizations have arisen before us, have reached our level of technological development, and have then, inevitably, destroyed themselves. The filter could be a global nuclear war, a runaway climate catastrophe, the development of a hostile superintelligent AI, or some other as-yet unforeseen technological trap. In this scenario, our own rapid technological progress is not a sign of our success, but a sign that we are approaching the same great filter that has extinguished all those who came before us. The Fermi paradox is not just an astronomical puzzle, it is a profound and deeply personal question about the future of our own species. It forces us to look in the mirror, to confront our own self-destructive tendencies, and to ask whether we have the wisdom and the foresight to navigate the immense challenges of our own technological adolescence. The answer to Fermi's simple, haunting question, "Where is everybody?" may be an answer that we ourselves will have to write, in the way we choose to shape our own and the planet's future. The discovery of thousands of exoplanets in the last 3 decades has been one of the most exciting and revolutionary developments in the history of astronomy. For millennia, the question of whether other stars had planets of their own was a matter of pure speculation. Now, we know that planets are not the exception, but the rule. Our galaxy is teeming with worlds, and the diversity of these worlds is far greater than we ever imagined. The techniques we use to find these distant planets are a testament to the incredible precision of modern astronomical instruments. The most successful of these is the transit method. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the starlight, causing a slight periodic dip in the star's brightness. Space telescopes like Kepler and TESS have monitored the brightness of hundreds of thousands of stars, looking for these telltale transits. The size of the dip tells us the size of the planet, and the time between the dips tells us the length of its year. The second major technique is the radial velocity, or Doppler method. As a planet orbits its star, its gravity causes the star to wobble slightly. This wobble can be detected as a small, periodic shift in the star's spectrum, a Doppler shift towards the red as the star moves away from us and towards the blue as it moves towards us. The size of the wobble tells us the mass of the planet. By combining these two methods, we can determine both the size and the mass of a planet, which allows us to calculate its density and to make an educated guess about its composition, whether it is a rocky world like Earth or a gas giant like Jupiter. These methods have revealed a veritable zoo of exoplanets, many of which have no analog in our own solar system. We have found hot Jupiters, massive gas giants orbiting incredibly close to their stars, with years that last only a few days and surface temperatures that can melt iron. We have found super-Earths, rocky worlds that are larger and more massive than our own planet, and mini-Neptunes, planets that are smaller than Neptune but larger than Earth, a class of planet that seems to be the most common type in the galaxy, yet is completely absent from our own solar system. We have found planets orbiting 2 stars, Tatooine worlds with double sunsets. We have found planets made of diamond, and planets where it might rain glass sideways. And most excitingly, we have found a growing number of potentially habitable, Earth-sized worlds, orbiting in the Goldilocks zone of their stars, the region where temperatures are just right for liquid water to exist on the surface. Systems like TRAPPIST-1, a star only 40 light-years away, host at least 7 rocky, Earth-sized planets, 3 of which are in the habitable zone. Proxima Centauri, our very nearest stellar neighbor, is now known to host at least 2 planets, one of which is a rocky world in the habitable zone. The next great frontier in exoplanet science is the study of their atmospheres. Using a technique called spectroscopy, we can analyze the starlight that has been filtered through a planet's atmosphere during a transit. The different molecules in the atmosphere absorb starlight at specific wavelengths, creating a unique absorption spectrum, a kind of chemical barcode. The James Webb Space Telescope is a master of this technique, and it is already providing us with unprecedented insights into the atmospheric composition of these distant worlds. It can detect the presence of water vapor, carbon dioxide, methane, and other gases, allowing us to begin to assess the potential habitability of these worlds and to search for the biomarkers, the chemical fingerprints of life. The discovery of exoplanets has transformed our view of the cosmos. We no longer see the stars as distant, lonely points of light. We see them as potential suns, the centers of other solar systems, each with its own unique family of worlds. And with each new discovery, the probability that we are not alone in this vast cosmic ocean seems to grow ever larger. The dream of interstellar travel, of journeying to the stars, is one of the oldest and most powerful aspirations of the human spirit. It is a dream that has fueled our science fiction, our art, and our deepest longings for exploration and discovery. But is it a dream that can ever become a reality? The primary and most daunting obstacle to interstellar travel is the sheer, unimaginable vastness of the distances involved. Our nearest stellar neighbor, Proxima Centauri is about 4.2 light-years away. This means that light itself, the fastest thing in the universe, takes over 4 years to make the journey. Our fastest current spacecraft, like the Parker Solar Probe, can reach speeds of a few hundred kilometers per second. At that speed, it would still take tens of thousands of years to reach Proxima Centauri. To make the journey in a reasonable amount of time, say, a human lifetime, we would need to build spaceships that can travel at a significant fraction of the speed of light. This would require propulsion systems that are far beyond our current technological capabilities. One of the most powerful and most terrifying concepts is Project Orion, a design from the 1950s that proposed propelling a large spacecraft by detonating a series of small, controlled nuclear explosions behind it. The explosions would push against a large pusher plate at the back of the ship, accelerating it to perhaps 10% of the speed of light. This would shorten the journey to Proxima Centauri to a more manageable 40 years. While the physics of Project Orion is sound, the engineering challenges, not to mention the political and environmental implications of launching a ship powered by thousands of nuclear bombs, are immense. More advanced and less destructive concepts include fusion propulsion, using the energy from controlled nuclear fusion to create a high-velocity plasma exhaust, or, even more exotically, antimatter propulsion, which would involve annihilating matter and antimatter to create the most efficient energy source possible. A recent and more plausible proposal is the Breakthrough Starshot Initiative, a project supported by Stephen Hawking and Yuri Milner. The idea is to use a powerful, ground-based laser array to accelerate a fleet of piece-gram-scale nanocrafts to about 20% of the speed of light. These star chips, equipped with a miniature camera, a power source, and a communication system, would be attached to a thin, reflective light sail. The intense laser beam from Earth would push on the sail, accelerating the nanocraft to incredible speeds in a matter of minutes. They could reach Proxima Centauri in about 20 years and send back images and data from another star system for the first time in human history. But even if we could solve the propulsion problem, interstellar travel faces a host of other challenges. At such high speeds, even a tiny speck of interstellar dust becomes a deadly projectile, capable of destroying the spacecraft. Advanced shielding or self-repairing systems would be essential. The long duration of the journey would also pose immense challenges for a human crew. The psychological effects of isolation and confinement, the biological effects of long-term exposure to zero gravity and cosmic radiation, are all major hurdles that would need to be overcome. This has led to the idea of generation ships, vast, self-sustaining space arcs that would carry a community of thousands of people on a multi-generational journey to the stars. The descendants of the original crew would be the ones to finally arrive at the destination, their ancestors having lived and died on the ship. An alternative to this would be to place the crew in a state of hibernation or cryogenic suspension, slowing down their metabolism to a crawl for the long duration of the journey. But these are technologies that are still firmly in the realm of science fiction, the most speculative and most exciting. Possibility for interstellar travel is the idea of manipulating space-time itself, of creating wormholes or warp drives that could provide a shortcut through the cosmos. These concepts, while allowed by the mathematics of general relativity, would require the existence of exotic matter with negative energy density, something that we do not know how to create or control. Despite all these immense challenges, humanity has already taken its first, timid steps into the interstellar void. The Voyager 1 and 2 probes, launched in 1977, have now crossed the heliopause, the boundary of our solar system, and are sailing through the uncharted territory of interstellar space. They are our first, and most distant, emissaries to the stars. While interstellar travel remains a distant, and perhaps even impossible, dream for now, it is a dream that continues to inspire us. It is a dream that pushes us to develop new technologies, to expand our understanding of the universe, and to think about the long-term future of our species. And it is a dream that is rooted in the same, deep, and fundamental human impulse that first led our ancestors to look up at the stars and wonder what lies beyond the horizon. The universe is a place of breathtaking beauty, of serene, celestial harmonies, but it is also a place of immense and often terrifying violence. The tranquil, unchanging appearance of the night sky is a profound illusion. The cosmos is a dynamic and often dangerous stage, filled with cosmic catastrophes that could, in principle, threaten the very existence of life on Earth. The most familiar, and perhaps most immediate, of these threats comes from our own celestial neighborhood, the asteroids and comets that are the leftover debris from the formation of our solar system. We know, from a wealth of geological evidence, that the Earth has been repeatedly bombarded by these objects throughout its history. 66 million years ago, an asteroid with a diameter of about 10 kilometers slammed into what is now the Yucatan Peninsula in Mexico. The impact released an amount of energy equivalent to billions of atomic bombs, triggering a global catastrophe that led to the extinction of the dinosaurs and about 75% of all species on the planet. And there is no reason to believe that such an event could not happen again. NASA and other space agencies are now actively engaged in a program of planetary defense, scanning the skies to identify and track any near-Earth objects, NEOs, whose orbits might bring them on a collision course with our planet. We have cataloged thousands of these objects, but there are likely many more, particularly smaller ones, that remain undiscovered. The good news is that we are developing the technology to defend ourselves. Missions like NASA's DART Double Asteroid Redirection Test have successfully demonstrated that we can change the orbit of an asteroid by crashing a spacecraft into it. If we can find a threatening object early enough, we have a real chance of deflecting it and avoiding a catastrophe. A more distant, but far more powerful, threat comes from the stars themselves. The death of a massive star in a supernova explosion is one of the most energetic events in the universe. If a supernova were to occur within a few tens of light years of the Earth, the consequences would be devastating. The intense burst of gamma rays and high-energy particles would strip away our protective ozone layer, bathing the surface in lethal ultraviolet radiation and potentially triggering a mass extinction. Fortunately, there are no stars in our immediate stellar neighborhood that are massive enough and close enough to the end of their lives to pose a significant threat. Even more powerful are gamma ray bursts, GRBs, the most luminous explosions in the cosmos. A GRB aimed at the Earth from within our own galaxy would be a civilization-ending event. But again, the probability of such an event is astronomically low. A more persistent, and perhaps more insidious, threat comes from our own sun. The sun is a star, and like all stars, it is a dynamic and sometimes violent object. It can unleash powerful solar flares and coronal mass ejections, CMEs, vast clouds of magnetized plasma that can wreak havoc on our technological infrastructure. A truly massive superflare, like the Carrington event of 1859, could, if it happened today, cause global power outages, destroy our satellite fleet, and cripple our modern, technology-dependent civilization for years. And then there are the long-term, and seemingly inescapable, cosmic fates. In about 5 billion years, our sun will exhaust the hydrogen fuel in its core and will begin to expand into a red giant phase. It will swell up to engulf the orbits of Mercury, Venus, and possibly the Earth itself. Even if our planet were to escape being directly swallowed, the intense heat from the bloated sun would boil away our oceans and render the surface completely uninhabitable. On an even grander timescale, our own Milky Way galaxy is on a collision course with our neighboring Andromeda galaxy. The merger, which will begin in about 4.5 billion years, will be a slow-motion cosmic catastrophe, a gravitational ballet that will reshape our galactic home over hundreds of millions of years. And finally, there is the ultimate fate of the universe itself. If dark energy continues to drive an accelerating expansion, the universe is destined for a big freeze, a slow, cold, and lonely death. These cosmic catastrophes, from the immediate threat of an asteroid impact to the distant entropic death of the cosmos, are a powerful and humbling reminder of our own fragility. We are a tiny, delicate species living on a small, precious world in a universe that is often indifferent and sometimes hostile to our existence. But this knowledge should not be a source of despair. On the contrary, it should be a powerful motivation. It should inspire us to cherish our planet, to work together as a species, and to develop the science and technology that will allow us to understand, and perhaps one day to mitigate, these cosmic threats. It is a call to become not just a planetary species, but a truly cosmic one, a species that has the wisdom and the foresight to ensure its own long-term survival in the vast, beautiful, and sometimes terrifying theater of the universe. In the quiet, contemplative moments when we gaze up at the starry sky, we are often struck by two seemingly contradictory feelings. On the one hand, there is the overwhelming sense of our own physical insignificance in the face of the sheer, unimaginable vastness of the cosmos. On the other hand, there is the equally powerful and deeply mysterious feeling of our own conscious significance. The feeling that we are not just passive observers, but are somehow, in a deep and fundamental way, connected to the very fabric of the reality we are observing. This is the great central paradox of the human condition, the paradox of our relationship with the universe. And at its heart lies one of the deepest and most profound mysteries in all of science and philosophy, the mystery of consciousness. How is it possible that a collection of non-conscious, physical matter, the atoms and molecules that make up our brains, can give rise to the rich, subjective, and qualitative world of our inner experience? The feeling of warmth from the sun on your skin, the taste of a ripe strawberry, the sound of a loved one's voice, the deep, poignant feeling of sorrow, the ineffable beauty of a sunset. These are the very stuff of our lives. And yet they seem to have no place in the objective, third-person world of our physical theories. This is what the philosopher David Chalmers has called the hard problem of consciousness. Science has made tremendous progress in understanding the easy problems of consciousness, the neural correlates of our mental states. We can map the brain activity associated with vision, with memory, with emotion, but we have no idea how or why this brain activity should be accompanied by a subjective, first-person experience at all. Why isn't it all just dark information processing, like in a sophisticated computer? This profound explanatory gap has led some scientists and philosophers to question the very foundations of our materialistic worldview. Perhaps consciousness is not an emergent property of complex computation, but is, in fact, a fundamental and irreducible property of the universe, on par with space, time, mass, and charge. This is the ancient idea of panpsychism, the view that some primitive form of mind or experience is present in all matter, from the smallest elementary particle to the largest galaxy. In this view, the universe is not a dead, mechanical thing that somehow, miraculously, gives rise to consciousness. The universe, at its core, is mental. Consciousness is not the exception, it is the rule. Our own complex human consciousness is just a particularly sophisticated and self-aware expression of this fundamental cosmic property. This idea, which has its roots in many of the world's spiritual and philosophical traditions, is now being taken seriously by a growing number of contemporary thinkers as a potential solution to the hard problem. Even more radical is the idea of cosmic consciousness, or idealistic monism, the view that consciousness is not just a property of the universe, but is the primary and ultimate reality itself. In this picture, the physical world is a manifestation, a projection, a dream within a single, universal mind. We are not separate, individual consciousnesses. We are all expressions of a single, cosmic consciousness, the Brahman of the Vedanta, or the mind of God of the mystics. In the quantum world, we find strange and beautiful echoes of these philosophical ideas. The role of the observer in collapsing the wave function, the non-local interconnectedness of entanglement, the participatory nature of reality suggested by John Wheeler, all of these seem to hint at a universe where mind and matter are not two separate things, but are two aspects of a single, deeper reality. Perhaps, as Carl Sagan famously said, we are a way for the cosmos to know itself. Our consciousness is not an alien presence in a dead universe. It is the universe's own, emergent capacity for self-awareness, for reflection, for wonder. We are made of stardust, the remnants of ancient, exploded stars, the carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the fiery hearts of stellar furnaces billions of years ago. We are, in the most literal and physical sense, children of the cosmos. And perhaps, in a deeper, more metaphysical sense, our minds are also children of the cosmos, tiny, precious windows through which the universe can begin to contemplate its own magnificent and mysterious existence. Our cosmic home, the Milky Way galaxy, is a vast and beautiful island of stars, a swirling, spiral city of light containing at least 200 billion suns. But it is just one island in an immense and perhaps infinite cosmic ocean. Beyond the boundaries of our own galaxy lies an intergalactic void of unimaginable scale, a darkness that is punctuated by the faint, distant light of other island universes. The nearest of these is the Andromeda Galaxy, a spiral galaxy that is even larger than our own, containing perhaps 1 trillion stars. It is located about 2.5 million light-years away, a distance so vast that the light we see from it tonight left that galaxy at a time when our own human ancestors were just beginning to walk upright on the plains of Africa. It is the most distant object that can be seen with the naked eye, a faint, fuzzy patch of light in the night sky, a ghostly reminder of the true scale of the cosmos. The Milky Way and Andromeda are the two dominant members of a small cluster of about 50 galaxies known as the Local Group. This group is, in turn, just one small part of a much larger structure, the Virgo supercluster, a vast collection of thousands of galaxies that stretches for over 100 million light-years. And even this supercluster is just a single node in the Laniakea supercluster, an even larger structure that contains about 100,000 galaxies and spans over 500 million light-years. When we map the distribution of galaxies on the largest scales, we find that they are not scattered randomly through space. They are arranged in a vast, intricate, and beautiful pattern, a cosmic web of long, interconnected filaments and dense, knot-like clusters, all surrounding vast, almost empty regions called cosmic voids. The largest of these structures, like the Sloan Great Wall, are filaments of galaxies that stretch for over 1 billion light-years. This cosmic web is a direct macroscopic manifestation of the tiny quantum fluctuations that were present in the very early universe, the seeds from which all this grand cosmic architecture has grown. The galaxies themselves come in a rich variety of shapes and sizes. There are the beautiful, spiral galaxies like our own, with their young, blue stars and their glowing arms of gas and dust. There are the giant, elliptical galaxies, huge, reddish balls of old stars, which are thought to be the product of the merger of smaller, spiral galaxies. And there are the small, irregular galaxies, often misshapen and chaotic, which are still in the process of active star formation. Some of these galaxies are far more active and violent than others. At the heart of many galaxies lies a supermassive black hole, and when this black hole is actively feeding on the surrounding gas and dust, it can release a tremendous amount of energy, outshining the entire host galaxy. These active galactic nuclei AGN are some of the most luminous objects in the universe. The most extreme of these are the quasars, AGN that are so bright that they can be seen from the very edge of the observable universe, their light having traveled to us for over 13 billion years. They are beacons from the cosmic dawn, allowing us to probe the conditions of the young, infant universe. The space between the galaxies, the intergalactic medium, is not completely empty. It is filled with a tenuous, hot gas, mostly hydrogen, which is the leftover raw material from the Big Bang that has not yet been incorporated into galaxies. And permeating this entire cosmic web, both within the galaxies and in the voids between them, is the invisible gravitational scaffolding of dark matter. The study of this large-scale structure, of the distribution and evolution of galaxies, is one of the most active and exciting frontiers of modern cosmology. By looking at distant galaxies, we are looking back in time, and we can piece together the story of how the universe has evolved, from a smooth, uniform state to the rich and complex tapestry of structures we see today. It is a story of gravitational collapse, of galactic mergers, of stellar birth and death, a story that is still unfolding all around us. And it is a story that has, over the course of 14 billion years, led to the formation of at least one small, blue planet in an unremarkable corner of one of a trillion galaxies. A planet that has given birth to a consciousness capable of looking out at this vast, cosmic panorama and beginning, however imperfectly, to understand its own profound and beautiful place within it. All things that have a beginning must, it seems, have an end. This is a truth that is woven into the very fabric of our own human experience, and it is a truth that seems to apply to the universe itself. The cosmos, in all its grandeur and complexity, is not an eternal, unchanging entity. It is an evolving, developing system, a system that is governed by the relentless and seemingly inescapable arrow of time. And this arrow points towards a final, ultimate fate. The second law of thermodynamics, the principle of increasing entropy, tells us that this universe as a whole is on a one-way journey from a state of low entropy, of high order and useful energy, to a state of maximum entropy, a state of complete disorder and thermal equilibrium, a state that physicists have chillingly dubbed the heat death. In this scenario, which is the one predicted by our current, standard cosmological model, the future of the universe is a long, slow, and gentle slide into a cold, dark, and empty oblivion. The story will unfold on timescales that are almost beyond our ability to comprehend. In about 100 trillion years from now, the era of star formation will come to a final end. The vast clouds of interstellar gas, the raw material for new stars, will have been exhausted. The last, faint, red dwarf stars, the longest-lived of all stars, will slowly flicker and die, their nuclear fires extinguished forever. This will mark the end of the stelliferous era, the age of stars in which we are currently living, the brief, luminous interlude that has made our own existence possible. The universe will then enter the degenerate era, a dark and silent cosmos populated only by the cold, dead remnants of stars, black dwarfs, neutron stars, and black holes. The galaxies themselves will begin to dissolve, their stellar corpses slowly being flung out into the ever-expanding intergalactic void through random gravitational encounters, over even more immense timescales, on the order of 10 to the power of 37 years. The very protons and neutrons that make up these degenerate objects may themselves decay, a prediction of some grand unified theories of particle physics. If this is the case, then all the baryonic matter in the universe will eventually disappear, leaving behind a thin, featureless soup of photons, neutrinos, electrons, and positrons. The only remaining structures will be the black holes, the great gravitational monuments to the universe's past glory, but even they are not eternal. Due to the quantum phenomenon of Hawking radiation, black holes will slowly, almost imperceptibly, evaporate, converting their immense mass back into a faint, thermal radiation. The most massive, supermassive black holes, with masses of billions of suns, will take an unimaginable amount of time to disappear, on the order of 10 to the power of 100 years, a Google years. But eventually, after a time so long that the entire current age of the universe is but an insignificant instant in comparison, the last black hole will evaporate in a final, faint flash of radiation. After that, the universe will enter its final, eternal state, the dark era. It will be a cold, dark, and almost perfectly empty void, filled only with a diffuse and ever redshifting gas of fundamental particles. The temperature will approach absolute zero. All structure, all complexity, all information will have been erased. This is the heat death, a state of perfect, timeless, and unchanging equilibrium. There are other, more dramatic, potential ends to our cosmic story. If dark energy is a phantom energy that grows stronger over time, the universe could end in a big rip, where the fabric of space-time itself is torn asunder, or if the expansion of the universe were to one day reverse, it could end in a big crunch, a fiery and violent collapse back into a singularity. There is also the unsettling possibility of a vacuum decay event, where a bubble of a new, more stable vacuum could expand at the speed of light and annihilate our entire reality. But the big freeze, the slow, gentle slide into entropic oblivion, is the fate predicted by our current, best understanding of the cosmos. It is a bleak and sobering vision, but even in this seemingly desolate future, there are glimmers of strange and speculative possibility. Some physicists have argued that in the infinite time of the dark era, random quantum fluctuations could, in principle, create new complex structures. Even a Boltzmann brain, a single, conscious observer with a full set of false memories. Others have speculated about the possibility of a Poincaré recurrence, the idea that in an infinite amount of time, any finite system must eventually return to a state arbitrarily close to its initial state, potentially triggering a new Big Bang. These are ideas that are on the very edge of science and philosophy, but they are a testament to our enduring human desire to find hope, to find a pattern of renewal, even in the face of a seemingly final and absolute end, for us. As beings of finite lifespan, these cosmic timescales are essentially an eternity. But the knowledge that our entire, glorious, and complex universe is just a temporary, fleeting firework display in the vast, dark expanse of cosmic time is a powerful source of both humility and perspective. It reminds us of the incredible preciousness of this brief, luminous moment we have been given. This rare and wonderful cosmic afternoon, when the universe is still young enough and ordered enough to have given birth to a consciousness capable of contemplating its own and the universe's ultimate and perhaps silent destiny. At the end of our long and winding cosmic journey, from the quantum foam of the primordial void to the cold, dark silence of the heat death, we are left to confront the most profound and personal question of all. What is our place in this vast and often terrifying cosmic theater? For most of human history, we have placed ourselves at the very center of the story. Our ancient mythologies and our geocentric cosmologies were a testament to our deep, intuitive sense of our own central importance. The universe, in this view, was created for us, and we were its most precious and significant inhabitants. But the last 500 years of scientific discovery have been a story of a great and often painful cosmic humiliation. The Copernican revolution moved us from the center of the universe to a small planet orbiting an ordinary star. The discovery of the vastness of the Milky Way galaxy in the early 20th century moved our sun from the center of the galaxy to an unremarkable location in one of its spiral arms. And the discovery of other galaxies, by Edwin Hubble, revealed that our own vast Milky Way is just one of trillions of other island universes in a vast and possibly infinite cosmic ocean. With each new discovery, our physical place in the cosmos has seemed to become more and more insignificant. We are, it seems, a fleeting and accidental byproduct of a blind, impersonal, and unimaginably vast universe. And yet, this is not the whole story, for there is another, equally valid perspective, a perspective that places us right back at the very heart of the cosmic drama. We are, as far as we know, the only beings in the universe who are capable of understanding its laws, of appreciating its beauty, of contemplating its meaning. A universe without a conscious observer, without a mind to witness it, would be like a magnificent symphony played in an empty hall, a breathtaking work of art painted in a locked and darkened room. Its beauty and its elegance would exist, but they would exist in a state of unmanifested potential, unseen, unheard, unknown. It is through the fragile and improbable instrument of our own human consciousness that the universe comes to know itself. As the great astronomer and science communicator Carl Sagan so eloquently put it, we are a way for the cosmos to know itself. We are the eyes through which the universe sees its own glory, the ears through which it hears its own music, the minds through which it contemplates its own deep mystery. This is not a position of physical centrality, but of a deeper, more profound, and more meaningful conscious centrality. This perspective has deep and beautiful implications. It tells us that our lives, however fleeting and insignificant they may seem on a cosmic scale, are not without meaning. Our joys, our sorrows, our struggles, our triumphs. These are not just personal, human dramas. They are part of the larger cosmic story, the story of the universe's own, long and arduous journey towards self-awareness, our quest for knowledge, our art, our music, our love. These are the universe's own creative expressions, its own way of exploring and celebrating its own infinite potential. We are, in the most literal sense, made of stardust. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the fiery hearts of long dead, massive stars, suns that lived and died billions of years before our own sun was born. We are the children of the cosmos, the inheritors of a 14 billion year-long legacy of cosmic evolution. This intimate, physical connection is a powerful reminder that we are not separate from the universe. We are a part of it. The laws of physics that govern the most distant galaxies are the same laws that govern the workings of our own bodies and brains. The cosmic drama is not something that is happening out there. It is happening in here, in the very fabric of our own being. And so, at the end of our journey, we are left with a beautiful and profound paradox. We are, at once, infinitesimally small and cosmically significant. We are the products of a blind, evolutionary process, and yet we are the bearers of a conscious awareness that can contemplate the very process that created us. We are ephemeral, mortal beings, and yet we are a part of a story that is as old as time itself, and perhaps our greatest value, our highest purpose, in this vast and possibly indifferent universe, is simply this: to be the witnesses, to look up at the night sky with a sense of wonder and awe, to ask the deep and perhaps unanswerable questions about our own existence, to create meaning, to find beauty, to love, to learn, and to pass on the torch of our curiosity and our knowledge to the generations that will follow us. In your eyes, which are at this very moment reading these words, the universe is looking at itself and contemplating its own magnificent and mysterious existence. And in this single, precious, and self-aware moment, the infinitely large meets the infinitely small, and the great cosmic circle of the story closes and begins anew.
Imagine a place where there is nothing, no light, no sound, no matter, not even the whisper of a single atom, an absolute void, a perfect emptiness. For centuries, this was our conception of space, a passive, silent stage upon which the drama of the cosmos unfolded. But what if this stage is not empty at all? What if the deepest, most profound silence is actually a roar of infinite potential? Modern physics has peeled back this veil of nothingness, and what it has revealed is one of the most unsettling and beautiful truths in all of science. The void is not empty. It is a seething, boiling ocean of energy, a phantom sea of constant creation and annihilation. This is the realm of zero-point energy, the hidden power of the universe, an invisible and inexhaustible reservoir that exists at every single point in space-time. It is the baseline hum of reality, the lowest possible energy state of the cosmos, a state which is, paradoxically, not zero. This is not a metaphysical speculation. It is a direct consequence of the laws of quantum mechanics. The uncertainty principle, first articulated by Werner Heisenberg, dictates that we can never know both the precise position and the precise momentum of a particle at the same time. This fundamental uncertainty extends to energy and time, in any field, in any system, even in a vacuum cooled to absolute zero. There must be a residual flicker of motion, an irreducible quantum jiggle. This is zero-point energy. It is the universe's insurance policy against absolute stillness, a law that decrees that nothing can ever truly be at rest. This constant vibration is not a chaotic or random noise. It is the fundamental symphony of the cosmos, a music that plays in the background of all existence. Every quantum field that makes up our reality, the electron field, the photon field, the Higgs field, is constantly vibrating, even in its ground state. These vibrations are not just a theoretical curiosity. They have real, measurable effects. They give rise to a constant stream of virtual particles. Phantom entities that borrow energy from the vacuum to pop into existence for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. We cannot see these particles directly, but we can see their shadows. The Casimir effect, where two uncharged metal plates in a vacuum are pushed together by an invisible force, is a direct, experimental confirmation of their existence. The pressure of the virtual particles outside the plates is greater than the pressure between them, creating a net force. The void itself can push and pull. This discovery transforms our understanding of reality. Matter is not a solid, fundamental substance, but an excitation, a ripple, a concentrated vibration in these underlying quantum fields. The space we perceive as empty is not a passive backdrop, but the very source of everything we see, the invisible foundation upon which the fabric of time, space, and matter is woven. To understand zero-point energy is to understand that what we call nothing is actually the most potent something in the universe, a sea of infinite possibility from which all of reality may have been born. The idea that energy can exist in a perfect vacuum, in what we intuitively understand as nothingness, is one of the most profound paradigm shifts in the history of science. It directly challenges our classical though common-sense understanding of the world. For centuries, our physics was built on the idea that energy is a property of things, of particles, of waves, of systems. The notion that energy could be a property of emptiness itself was unthinkable. Yet, the evidence is undeniable. The Casimir effect is not a subtle, theoretical correction. It is a measurable, physical force that can be detected in a laboratory. It is the macroscopic manifestation of the microscopic quantum foam, a direct testament to the fact that the void is alive with energy. But if this energy is real, where is it, and can we use it? This is where the mystery deepens. Zero-point energy is not like the energy stored in a battery or in a gallon of gasoline. It is a uniform, isotropic energy that pervades all of space. There is no gradient, no difference in potential that would allow us to easily extract it. To use energy, we need to create a flow from a high-energy state to a low-energy state, but zero-point energy is already the lowest possible energy state of the system. It is like trying to get water to flow out of the bottom of the ocean, and yet, the sheer amount of this energy is staggering. When physicists attempt to calculate the energy density of the quantum vacuum based on the principles of quantum field theory, they arrive at a number that is astronomically large. It is an energy density so immense that, if it were all gravitationally active in the way that normal matter and energy are, the universe would have collapsed into a black hole in the first fraction of a second of its existence. This enormous discrepancy between the theoretical calculation and the observed reality of our universe is known as the cosmological constant problem, or the vacuum catastrophe, and it is arguably the single greatest unsolved problem in all of fundamental physics. It tells us that there is something profound about the nature of vacuum energy that we do not yet understand. Perhaps there is a hidden symmetry of nature, a principle of supersymmetry, for example, where the contributions of different types of particles to the vacuum energy precisely cancel each other out, leaving only a tiny residual amount. Or perhaps our understanding of gravity itself is incomplete, and the vacuum energy does not gravitate in the same way as normal matter. Whatever the solution, the reality of this vacuum energy is not in doubt. Its most significant consequence may be playing out on the largest possible scales. The observed accelerating expansion of the universe, attributed to a mysterious dark energy, is one of the great puzzles of modern cosmology. The properties of this dark energy, a constant energy density that does not dilute as the universe expands, are remarkably similar to the properties of the vacuum energy predicted by quantum mechanics. Many cosmologists now believe that dark energy is, in fact, the macroscopic manifestation of zero-point energy, the faint, residual energy of the vacuum acting as a cosmic anti-gravity, pushing the universe apart. If this is true, then the fate of our cosmos, its ultimate journey into an ever-expanding, cold and dark future, is being dictated by the subtle, incessant quantum vibrations of empty space. The greatest mystery on the cosmological scale may have its roots in the deepest secrets of the quantum void. The allure of an infinite, ubiquitous energy source has inevitably captured the human imagination. giving rise to a subculture of invention, speculation, and science fiction centered on the idea of harnessing zero-point energy, the concept of free energy, of a device that can extract limitless power from the vacuum, has been a holy grail for inventors and theorists for decades. Patents have been filed, prototypes have been built, and countless claims have been made, often blurring the line between legitimate scientific inquiry and pseudoscience. The core idea behind many of these proposed devices is to create a localized asymmetry in the vacuum, a way to tap into the zero-point fluctuations and convert them into usable work. This is often imagined through resonant cavities or specially designed nanostructures that could, in theory, interact with the virtual particles of the vacuum, much like a windmill interacts with the wind. The Casimir effect itself is often cited as a proof of principle. If the vacuum can exert a physical force, then in principle, that force can be used to do work. A hypothetical Casimir engine might involve two plates that are cyclically brought together and pulled apart, with the attractive Casimir force doing work in one part of the cycle. However, the scientific and engineering challenges are immense. The Casimir force is incredibly weak and only becomes significant at nanometer scale separations. Building a macroscopic engine that could overcome friction and other dissipative forces to extract a net positive amount of energy remains far beyond our current technological capabilities. Furthermore, there is a deep theoretical objection rooted in the laws of thermodynamics. The second law of thermodynamics, the law of entropy, states that you cannot build a perpetual motion machine of the second kind, a machine that extracts heat from a single thermal reservoir and converts it entirely into work. The quantum vacuum, in many ways, behaves like a thermal reservoir at absolute zero. Extracting energy from it would seem to violate this fundamental principle. Most mainstream physicists argue that while zero-point energy is real, it is the ground state of the universe, and you cannot extract energy from the ground state, just as you cannot get water to flow from the lowest point in a valley. Yet, the debate continues. Some researchers argue that the quantum vacuum is not a simple thermal system and that the classical laws of thermodynamics may not apply in the same way. They propose that through clever engineering, it might be possible to create a non-equilibrium state, a way to pump the vacuum to extract its energy. These ideas remain highly speculative and are on the very fringes of accepted physics, but they speak to a deep human desire, the desire for a clean, limitless, and universally available source of power. The story of zero-point energy is, in this sense, a modern myth. It is the story of a hidden cosmic power, a secret fire that, if it could be stolen from the gods of quantum mechanics, would transform human civilization forever. While the scientific consensus remains skeptical, the dream persists, and perhaps it is a necessary dream. The quest to understand and potentially harness zero-point energy, even if it ultimately proves impossible, is pushing the boundaries of our understanding of quantum mechanics, nanotechnology, and the very nature of energy itself. It is a quest that forces us to ask fundamental questions about the relationship between energy, information, and the structure of the vacuum. And in science, sometimes the questions are more important than the answers. While the dream of harnessing zero-point energy for power remains in the realm of speculation, its real, measurable effects are already shaping our world in tangible ways. The Casimir effect, once a theoretical curiosity, has become a crucial consideration in the field of micro and nano-electromechanical systems. At the scale of microns and nanometers, where the components of tiny machines are separated by incredibly small distances, the Casimir force is no longer negligible. In fact, it can become a dominant force, causing microscopic cantilever beams to stick to their substrates, a phenomenon known as stiction. For engineers designing these tiny devices, the Casimir force is a very real and often problematic aspect of the physical world that they must account for in their designs. They must develop special coatings and surface geometries to mitigate its effects. But what was once a problem is now being seen as a potential opportunity. Researchers are now exploring ways to engineer and control the Casimir force, to turn this invisible quantum pressure into a tool. By carefully designing the shape and material properties of surfaces, it is possible to modify the spectrum of zero-point fluctuations between them. and thus to tune the Casimir force. It is possible to make it repulsive instead of attractive, or to create a Casimir torque that can cause microscopic objects to rotate. This has opened the door to a new generation of nanotechnology based on quantum engineering of the vacuum. Imagine tiny, frictionless bearings that levitate on a cushion of repulsive Casimir force, or microscopic actuators driven by the modulated pressure of the quantum vacuum. These are not science fiction, they are active areas of experimental research. The Casimir effect provides us with a direct, albeit subtle, handle on the energy of the void. It is our first, tentative step towards interacting with and manipulating the most fundamental energy field in the universe. This has profound philosophical implications. We are not just passive observers of the quantum world, we are learning to become active participants, to engineer the very fabric of emptiness. The effect is also a powerful pedagogical tool, a stark and beautiful demonstration that our intuitive, classical understanding of the world breaks down its small scales. It is a window into the quantum realm, a glimpse of a reality that is far stranger and more counterintuitive than our everyday experience would lead us to believe. The invisible force between two plates in a vacuum is a testament to the fact that the universe is governed by laws that are often hidden from our direct perception. Laws that can only be uncovered through the combined power of theoretical insight and precise experimentation. The Casimir effect is more than just a clever experiment. It is a bridge between the abstract, mathematical world of quantum field theory and the concrete, physical world of force and motion. It is where the ghost-like dance of virtual particles becomes a real, measurable pressure, a pressure that is already being incorporated into the design of our most advanced technologies, and may one day be the driving force behind the machines of the future. The quantum vacuum is not just a stage for the fleeting dance of virtual particles. It is the very foundation upon which all of matter is built. Our classical picture of matter is one of solid, inert particles, like tiny billiard balls. But quantum field theory tells us that this picture is fundamentally wrong. A fundamental particle, like an electron, is not a solid object. It is a localized, vibrating excitation of a more fundamental entity, the electron field. This field, like all quantum fields, pervades all of space-time. The particle we perceive as an electron is simply a place where this field is vibrating with a certain quantized amount of energy. When the field is not excited, when it is in its ground state, we perceive it as empty space. But even in this ground state, the field is still there, and it is still subject to the incessant zero-point fluctuations. This has profound consequences for the nature of matter. The electron is not an isolated entity. It is in constant, intimate interaction with the quantum vacuum. It is continuously emitting and reabsorbing virtual photons, the carriers of the electromagnetic force, dressing itself in a cloud of these phantom particles. This vacuum polarization effectively screens the electron's bare charge, meaning the electric charge we measure is not its true, intrinsic charge, but a value that has been modified by its interaction with the void. Similarly, the mass of a particle is not an intrinsic, fixed property. A significant portion of a particle's mass arises from its interaction with the various quantum fields that fill the vacuum. The Higgs field, for example, permeates all of space, and particles acquire mass by dragging against it. But even beyond the Higgs mechanism, the self-interaction of a particle with its own field, mediated by the virtual particles of the vacuum, contributes to its measured mass. In a very real sense, matter is bootstrapped into existence by its own interaction with the emptiness that surrounds it. This dynamic, energetic picture of matter helps to explain some of its most fundamental properties. The stability of atoms, for instance, is a quantum mechanical phenomenon that depends on the vacuum. In classical physics, an electron orbiting a nucleus should radiate away its energy and spiral into the center in a fraction of a second. The reason this does not happen is that the electron can only exist in specific quantized energy levels. These levels are determined by the electron's wave-like nature and its interaction with the electromagnetic vacuum. The lowest energy level, the ground state, is not at zero energy. It is a state of dynamic equilibrium with the zero-point fluctuations of the vacuum. The electron cannot fall any lower because there is no lower energy state available to it. The atom is stable because the void itself provides a floor. a baseline of energy below which it cannot go. This understanding has cosmological implications as well. The very first seeds of structure in the universe, the tiny density fluctuations that would later grow into galaxies and clusters of galaxies, are thought to have originated as quantum fluctuations in the vacuum during the period of cosmic inflation. The quantum foam of the early universe was stretched to astronomical scales by the rapid expansion, freezing these microscopic fluctuations into the macroscopic seeds of all the structure we see today. The universe is, in a very real sense, a macroscopic manifestation of the quantum vacuum. We live inside a frozen snapshot of the void's primordial turbulence. This completely inverts our traditional view of the relationship between matter and space. We no longer see space as a passive container for matter. Instead, we see matter as an emergent property of space, a temporary localized ripple on the surface of a deep and energetic quantum sea. The invisible foundation is the true reality. The solid world we perceive is just its fleeting expression. The relationship between zero-point energy and the laws of thermodynamics is one of the most challenging and debated topics in modern physics, highlighting a deep, unresolved tension between our understanding of the quantum world and the macroscopic world of heat and energy. The laws of thermodynamics are some of the most robust and universal principles in science. The first law, the conservation of energy, states that energy cannot be created or destroyed, only transformed. The second law, the law of entropy, states that the total disorder of a closed system always increases over time. The third law states that it is impossible to reach absolute zero temperature in a finite number of steps. Zero-point energy seems to sit uncomfortably with all of these. At first glance, the constant emergence of virtual particles from the vacuum seems to violate the first law. Where is this energy coming from? The answer, within the framework of quantum mechanics, lies in the energy-time uncertainty principle. Energy can be borrowed from the vacuum for a very short amount of time, as long as it is paid back quickly. The virtual particles are this borrowed energy, and their brief existence and subsequent annihilation ensure that, on average, energy is conserved, so the first law holds. But in a strange, probabilistic quantum mechanical way, the real tension lies with the second and third laws. The third law states that as a system approaches absolute zero, its entropy approaches a minimum value, and all motion should cease. But zero-point energy dictates that quantum systems can never be completely at rest. Even at absolute zero, there is a residual energy and a residual quantum fluctuation. This does not necessarily contradict the third law, as the law is about the process of reaching absolute zero, but it does challenge our classical intuition about what absolute zero means. It is not a state of perfect stillness, but a state of minimum possible quantum motion. The deepest conflict is with the second law, the law of entropy. The second law is what gives time its arrow. It is why heat flows from hot to cold, why eggs break but do not unbreak, why our universe evolves from a state of order to a state of disorder. But zero-point energy seems to be a form of energy that is perfectly ordered and does not dissipate. It is a constant, coherent hum that does not seem to be subject to the relentless march of entropy. If we could extract this energy, we could theoretically build a machine that would run forever, seemingly violating the second law. Most physicists resolve this by arguing that zero-point energy is a non-thermal energy. It is not heat, and it cannot be used to do work in the same way as a hot gas. It is the ground state, and you cannot extract energy from the ground state. However, this raises a deeper question. If there is this vast reservoir of perfectly ordered entropic energy pervading the universe, why does the universe as a whole still seem to obey the second law? This tension may be a clue that our understanding of thermodynamics is incomplete. Classical thermodynamics was developed to describe systems of steam engines and gases. It may not be the final word on the thermodynamics of the quantum vacuum itself. Some theorists have proposed new frameworks, like quantum thermodynamics, that attempt to generalize the laws of heat and energy to the quantum realm. In these frameworks, concepts like entropy and temperature are redefined to account for quantum effects like entanglement and superposition. The resolution of the conflict between zero-point energy and thermodynamics is a work in progress, but it is a crucial one. It lies at the heart of our attempts to build a unified theory of physics, one that can describe both the microscopic world of quantum mechanics and the macroscopic world of our everyday experience. It is a puzzle that connects the deepest questions about the nature of energy, the arrow of time, and the ultimate fate of the universe. The puzzle of the universe's expansion is another area where zero-point energy takes center stage, acting as the prime suspect in one of cosmology's greatest mysteries. The discovery in the late 1990s that the expansion of the universe is not slowing down under the pull of gravity, but is in fact accelerating, was a profound shock to the scientific community. It implied the existence of a mysterious, repulsive force, a form of dark energy that is pushing the cosmos apart. The nature of this dark energy is completely unknown, but its properties are strangely familiar. It appears to be a form of energy that is inherent to space-time itself, with a constant energy density that does not dilute as the universe expands. This is exactly the behavior we would expect from the zero-point energy of the quantum vacuum. And so, the leading hypothesis is that dark energy and vacuum energy are one and the same. The silent, incessant hum of the quantum void is the engine driving the cosmic acceleration. This is a beautifully elegant and simple idea. It connects the largest scale phenomenon in the universe, its accelerating expansion, with the smallest scale phenomenon, the quantum fluctuations of the vacuum. It suggests that the fate of the cosmos is being written by the laws of subatomic physics. If this hypothesis is correct, then zero-point energy is not just a subtle and microscopic effect, it is the most dominant form of energy in the universe. Making up roughly 70% of the total cosmic energy budget, it is the invisible, the silent majority that is shaping the future of our reality. In this picture, the future is one of eternal expansion. As the universe grows larger, the density of matter and radiation will continue to decrease, while the density of vacuum energy remains constant. Eventually, vacuum energy will be the only significant component of the universe. Galaxies will recede from each other at ever-increasing speeds, eventually disappearing beyond our cosmic horizon. The universe will become an increasingly cold, dark, and lonely place, a scenario known as the Big Freeze. It is a future dictated by the relentless, repulsive pressure of the void. However, as we have seen, this elegant picture is marred by the cosmological constant problem, the colossal discrepancy between the theoretical calculation of the vacuum energy and the observed value. This discrepancy is so large that many physicists believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps the problem lies not with the energy of the vacuum, but with our understanding of gravity. Maybe general relativity needs to be modified on cosmological scales, giving rise to an apparent acceleration without the need for any new form of energy. These are all active areas of research, and the James Webb Space Telescope is providing crucial data to help distinguish between them by precisely measuring the expansion history of the universe at different epochs. Webb can help to determine if the properties of dark energy have changed over time. The nature of the universe's expansion is one of the most fundamental questions in all of science, and at its heart lies the enigmatic nature of the void, zero-point energy. Whether it is the silent engine of cosmic acceleration or a red herring in the search for dark energy, is a concept we must grapple with to understand our cosmic destiny. It is a puzzle that connects the beginning of the universe with its end, the quantum with the cosmos, and the deepest secrets of the void with the ultimate fate of all that we know. The quantum vacuum is not just a passive energy reservoir, it is a dynamic, creative medium, a quantum foam where the very fabric of space-time is thought to be in a constant state of turmoil at the smallest possible scales. This concept, first envisioned by the physicist John Archibald Wheeler, takes the implications of the uncertainty principle to their logical extreme. If the energy of a field can fluctuate over short timescales, and if energy and mass are equivalent, then these energy fluctuations can, in principle, create tiny, fleeting curvatures in space-time. At the Planck scale, the incredibly small scale of 10 to the power of minus 35 meters, where the effects of quantum mechanics and gravity are thought to become equally important, space-time is no longer a smooth, a continuous manifold. Instead, it is a roiling, chaotic foam of tiny, transient wormholes and microscopic black holes, constantly bubbling into and out of existence. In this picture, the smooth space-time of our macroscopic experience is just an average, a large-scale approximation of a much more violent and chaotic underlying reality. The quantum foam is a direct consequence of the zero-point energy of the gravitational field itself. Just like the electromagnetic field, the gravitational field has a ground-state energy, and its zero-point fluctuations are what create this foamy structure. This idea has profound implications for our understanding of reality. It suggests that the concepts of distance and duration, which seem so fundamental to us, may break down at the Planck scale. The very notions of here and there, before and after, may lose their meaning in this quantum fuzziness. Time itself may not be a continuous flow, but a series of discrete probabilistic jumps, a staccato rhythm played out on the foamy stage of the quantum vacuum. This is a radical departure from the smooth, continuous spacetime of Einstein's general relativity, and it is at the heart of the search for a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. But the quantum foam is not just a theoretical playground for physicists. It may have real, cosmological consequences. Some theories propose that our entire universe may have originated as a single, large quantum fluctuation in a pre-existing quantum foam, a bubble that spontaneously nucleated and then rapidly expanded in the event we call the Big Bang. In this scenario, the universe is not a unique creation, but a natural, and perhaps common, outcome of the inherent restlessness of the void. This leads to the tantalizing idea of a multiverse, a vast ensemble of bubble universes, each with its own physical laws and constants, constantly budding off from an eternally inflating quantum foam. Our universe is just one bubble among many, a fortunate fluctuation where the conditions happen to be right for the emergence of stars, galaxies, and life. This is a speculative but powerful idea, as it provides a potential explanation for the apparent fine-tuning of our own universe's physical constants. We live in a universe that is hospitable to life because we could not live in one that wasn't. We are the survivors of a cosmic lottery. The concept of the quantum foam, born from the simple idea of zero-point energy, thus leads us to the grandest and most mind-bending of all cosmological ideas. It suggests that our entire reality, with all its vastness and complexity, may be nothing more than a temporary, fortunate ripple on the surface of an infinite, eternal, and endlessly creative quantum sea. The emptiness is not just the foundation of matter, it is the womb of worlds. The creative potential of the void, its ability to birth particles and perhaps even universes, is mirrored by its potential to act as a force of anti-gravity, a concept that has long been a staple of science fiction, but which finds a tentative, theoretical grounding in the physics of zero-point energy. Our classical understanding of gravity, as described by Newton and refined by Einstein, is that it is always an attractive force, mass and energy curve space-time. And this curvature tells other mass and energy how to move, always pulling them together. But the accelerating expansion of the universe tells us that there must be a repulsive force at play on cosmological scales, a form of cosmic anti-gravity. As we have seen, the leading candidate for this is the zero-point energy of the vacuum. The key lies in the concept of negative pressure. In normal matter, pressure is a positive quantity that acts as a source of gravitational attraction alongside its mass energy. But a field with a constant energy density, like the quantum vacuum, has a strange and counterintuitive property. Its pressure is negative, and it is equal in magnitude to its energy density. When you plug this negative pressure into Einstein's equations of general relativity, it creates a gravitational repulsion. The void, in a sense, pushes itself apart. This is the theoretical basis for the anti-gravity effect of zero-point energy. While this effect is currently only observed on the vast scales of the cosmos, It has ignited speculation about the possibility of harnessing this phenomenon for technological purposes. If we could somehow engineer a region of space to have a much higher density of vacuum energy, or if we could manipulate the properties of the vacuum itself, could we create a localized anti-gravity field? This is the dream of warp drive and other exotic propulsion systems. A hypothetical warp drive, like the one proposed by the physicist Miguel Alcubierre, would not work by accelerating a spaceship through space, but by manipulating space-time itself. It would involve creating a bubble of space-time around the ship, contracting space in front of it and expanding space behind it. The ship itself would remain stationary within this bubble, while the bubble moves through space, potentially at superluminal speeds, without violating the local speed of light limit. The energy requirements for such a device, according to the original calculations, were astronomical, requiring more energy than exists in the entire visible universe. However, more recent theoretical work has suggested that by cleverly designing the shape of the warp bubble, the energy requirements could be drastically reduced, perhaps to the mass of a large planet. The problem is that these models still require the existence of exotic matter with negative energy density. And while the Casimir effect does demonstrate a region of lower than normal vacuum energy, creating a macroscopic amount of stable, negative energy is far beyond our current capabilities and may be forbidden by the laws of physics. Despite these immense challenges, the anti-gravity potential of zero-point energy remains a tantalizing, if distant, possibility. It represents the ultimate technological ambition to graduate from being passengers on the currents of space-time to becoming its pilots. It is a dream that connects the deepest questions of quantum gravity with our most profound aspirations for a future among the stars. It is a reminder that the void is not just a source of cosmic expansion, but also a source of endless human imagination, a canvas upon which we project our hopes for a future where even the laws of gravity may one day be subject to our command. The symphony of the cosmos is played on an orchestra of quantum fields, and zero-point energy is its fundamental tuning note, the silent, ever-present hum against which all other melodies are played. This is not just a poetic metaphor, it is a deep physical truth. The properties of all the fundamental particles and forces in the universe are intimately tied to the properties of the quantum vacuum. The universe is not a collection of independent entities, but a holistic, interconnected system. And zero-point energy is the energetic medium that connects it all. Consider the very constants of nature, the charge of the electron, the strength of the fine structure constant, the mass of the Higgs boson. In our current theories, these are fundamental parameters that we must measure experimentally. We do not know why they have the values they do, but in a deeper, more complete theory, these constants may not be fundamental at all. They may be emergent properties of the vacuum, determined by the complex interplay of all the zero-point fluctuations of all the quantum fields. The values we measure may be the result of a cosmic settlement, an equilibrium state that the universe has fallen into. This is the idea behind theories like string theory, which posits that all the fundamental particles are just different vibrational modes of a single, underlying entity, a tiny, vibrating string. In this picture, the properties of the particles are determined by the way the string vibrates, which is in turn determined by the geometry of the extra, hidden dimensions of spacetime that string theory requires. The shape and size of these extra dimensions are properties of the vacuum, and thus the laws of physics themselves are a consequence of the vacuum structure. This leads to the stunning possibility that the laws of physics may not be universal in an absolute sense. If our universe is just one bubble in a multiverse, as the quantum foam concept suggests, then other bubble universes could have different vacuum states, different geometries for their extra dimensions, and therefore different physical laws. This provides a potential solution to the fine-tuning problem. The reason the constants of nature in our universe appear to be so finely tuned for the existence of life is because we live in one of the few universes where they are. In the vast cosmic symphony, there are countless dissonant, lifeless universes. We simply inhabit one of the rare, harmonious ones. This perspective transforms zero-point energy from a simple background noise into the very DNA of the cosmos, the source code that specifies the laws and constants of our reality. The silent notes of the vacuum are what determine the music of existence. The quest to understand zero-point energy is therefore not just a quest to understand a particular form of energy, it is a quest to understand the operating system of the universe. It is a search for the deepest logic of reality, the why behind the what. And as we listen more closely to the silent hum of the void, with instruments like the James Webb Space Telescope and the next generation of particle accelerators, we may begin to discern the structure of this cosmic score, to understand the principles that govern its harmony, and to perhaps, one day, learn to play a few notes of our own. The universe is a symphony, and we are the part of the symphony that has woken up and is beginning to listen to itself. It is the most profound and beautiful endeavor in all of human history. The profound interconnectedness of the quantum vacuum raises one of the most speculative, yet deeply compelling questions at the intersection of science and philosophy. Could there be a link between the zero-point energy field and the phenomenon of consciousness? This is a question that pushes the boundaries of scientific inquiry, venturing into territory that is often dismissed as mystical or pseudoscientific. And yet, the strange, non-local, and holistic nature of both the quantum vacuum and consciousness invites us to at least consider the possibility of a connection. Quantum mechanics has taught us that the universe is not a collection of separate, independent objects, but a web of interconnected probabilities. The observer effect, where the act of measuring a quantum system forces it to collapse from a state of multiple possibilities into a single, definite reality, has long suggested that consciousness may play a more active role in the universe than classical physics would allow. While most physicists interpret the observer effect as a result of the interaction of the quantum system with a macroscopic measuring device, and not necessarily with a conscious mind, a minority have long argued for a more direct role for consciousness. The theory of orchestrated objective reduction, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is one of the most well-developed of these models. It posits that consciousness arises from quantum computations occurring within microtubules, the protein skeletons of our brain's neurons. In this model, these quantum computations are not isolated. They are coupled to the zero-point fluctuations of the vacuum, the fundamental geometry of space-time. Consciousness, in this view, is a process of orchestrated collapse of the quantum wave function, a process that is not random, but is influenced by a form of Platonic information embedded in the Planck scale structure of the universe. The conscious mind, in a sense, is tapping into the fundamental information field of the cosmos, a field whose energetic manifestation is the zero-point energy. This is a highly speculative and controversial theory, and it lacks direct experimental evidence, but it is a scientifically testable one. It makes specific predictions about the quantum properties of the brain that could, in principle, be measured. But even beyond specific models like OR, the general idea of a connection between the vacuum field and consciousness resonates with many philosophical and spiritual traditions. The concept of a universal consciousness, a Brahman in Hinduism or a Tao in Taoism, a fundamental unified field of awareness from which all individual consciousness arises, has echoes in the modern physical concept of a unified quantum field that pervades all of space. Could the zero-point energy field be the physical correlate of this ancient philosophical idea? Could it be the interface between mind and matter, the medium through which intention and awareness can have a subtle but real influence on the physical world? This is a question that science is not yet equipped to answer, but it is a question that is becoming increasingly legitimate to ask. As our understanding of both the brain and the quantum vacuum deepens, we may find that the hard line we have drawn between the inner world of subjective experience and the outer world of objective reality is not as solid as we thought. Perhaps they are two sides of the same coin, two different manifestations of the same underlying information-rich and endlessly creative quantum reality. The possibility that the silent energy of the void is connected to the silent inner world of our own consciousness is a thought of breathtaking scope. It suggests that we are not just observers of the cosmic symphony, but are, in the most profound sense, an integral part of the music itself. Our thoughts, our feelings, our very awareness may be a resonance, a specific complex vibration of the same fundamental field that gives birth to stars and shapes the destiny of the universe. The technological implications of understanding and potentially manipulating the quantum vacuum are as vast as the cosmological ones. The development of quantum computers, for example, is a field that is both limited by and potentially empowered by zero-point energy. Quantum computers derive their immense processing power from their ability to harness the strange principles of the quantum world, like superposition and entanglement. A quantum bit, or qubit, can exist in a superposition of both 0 and 1 at the same time, allowing a quantum computer to explore a vast number of possibilities simultaneously. But this quantum fragility is also their Achilles' heel. Qubits are incredibly sensitive to their environment. Any stray interaction, any unwanted noise, can cause the delicate superposition to collapse, a process called decoherence, which destroys the quantum computation. And the most fundamental source of noise in the universe is the zero-point fluctuations of the quantum vacuum. The constant, random jiggle of the vacuum fields is a persistent background hiss that quantum engineers must constantly battle. They must develop sophisticated error correction codes and shielding techniques to protect their qubits from the inherent restlessness of the void. In this sense, zero-point energy is the ultimate adversary in the quest to build a large-scale, fault-tolerant quantum computer. But what if we could turn this adversary into an ally? Some theorists have proposed that it might be possible to engineer the vacuum itself, to create squeezed vacuum states where the quantum noise is reduced in one variable at the expense of increased noise in another. This could be used to create a quieter environment for qubits to operate in, pushing the limits of quantum computation. Even more speculatively, the quantum vacuum could one day become the ultimate communication medium. The phenomenon of quantum entanglement, where two particles can remain connected in such a way that a measurement on one instantly influences the other, regardless of the distance between them, seems to defy our classical notions of space and time. While it is not possible to use entanglement to send information faster than light, it does suggest a deep, non-local connectivity inherent in the fabric of reality. Some have speculated that it might be possible to modulate the vacuum state itself, to create vacuum telegraphs that could transmit information through the zero-point field. This would be a form of communication that does not involve the transmission of any particles or energy in the classical sense, but rather the propagation of a change in the state of the vacuum. Such a technology, if it were ever possible, would be truly revolutionary, offering a secure and potentially instantaneous form of communication across vast distances. The relationship between quantum information and the vacuum is a rich and complex one. It is a field where the deepest questions of fundamental physics meet the most practical challenges of next-generation technology. As we learn to build machines that can operate at the quantum level, we are also learning to interact with the universe in a new way, to speak its native language of probability, superposition, and entanglement. And in this dialogue with the quantum world, the silent, ever-present energy of the void is a constant partner, a source of both challenge and opportunity, the ultimate frontier for both our understanding and our technological ambition. The influence of the quantum vacuum is not confined to the exotic realms of quantum computing or cosmology. It leaves it subtle but detectable, fingerprints on the very properties of the light and radiation that fill our universe. Light, in the classical picture, is an electromagnetic wave that propagates through a passive, empty space. But in the quantum picture, light is a stream of photons, and the space it travels through is a dynamic, fluctuating medium. The interaction between photons and the zero-point fluctuations of the vacuum leads to a number of fascinating and subtle effects. One of these is the phenomenon of vacuum birefringence, a prediction of quantum electrodynamics that has yet to be definitively observed. In the presence of a very strong magnetic field, the vacuum itself is predicted to behave like a birefringent crystal, meaning it would have a different refractive index for light of different polarizations. A beam of unpolarized light passing through such a magnetized vacuum would emerge slightly polarized. This effect is caused by the strong magnetic field influencing the behavior of the virtual electron-positron pairs that are constantly popping in and out of the vacuum. The field aligns their spins, effectively giving the vacuum a grain or an axis that affects the light passing through it, while the effect is incredibly small. Astronomers are searching for it in the light from magnetars, the neutron stars with the strongest magnetic fields in the universe. A confirmed detection of vacuum birefringence would be a stunning confirmation of one of the most counterintuitive predictions of QED, and a direct testament to the physical reality of the virtual particles of the vacuum. Another, more subtle, effect is the potential for the vacuum to influence the speed of light itself. According to Einstein's theory of relativity, the speed of light in a vacuum is a universal constant. However, some theories of quantum gravity suggest that at the Planck scale, the foamy, fluctuating nature of spacetime could affect the propagation of light. High-energy photons, with wavelengths approaching the Planck length, might interact more strongly with the spacetime foam, causing them to travel slightly slower than low-energy photons. This would be a tiny, energy-dependent violation of Lorentz invariance, the fundamental principle of relativity that underpins all of modern physics. Astronomers are searching for this effect by looking at the arrival times of high-energy photons from distant gamma-ray bursts. If high-energy photons from a burst consistently arrive slightly later than low-energy photons from the same burst, it could be a sign of this quantum gravity effect. So far, no such effect has been detected, which places tight constraints on many of these theories. But the search continues. These are incredibly challenging measurements, pushing the limits of our observational capabilities, but they are crucial. The light that travels to us across billions of light years from the distant universe is not just a picture of the past, it is a probe, a messenger that has traveled through the quantum vacuum for eons, carrying with it subtle imprints of its journey. By carefully deciphering these imprints, by looking for tiny changes in polarization, speed, or direction, we can use the light from the cosmos to study the properties of the void itself. It is a beautiful irony that by studying the brightest objects in the universe, we can learn about the nature of its deepest darkness, and by analyzing the properties of light, we can probe the very substance of emptiness. The vast, cold, and seemingly empty cosmic voids, the great deserts of the cosmos, are being transformed by our understanding of zero-point energy from places of nothingness into laboratories of fundamental physics. These are the most pristine regions of the universe, where the density of matter is so low that the effects of the quantum vacuum are not drowned out by the noise of stars, gas, and galaxies. It is here, in the deepest silence, that we can best hope to listen to the hum of the void. The existence of these voids is a natural consequence of the gravitational instability that drives the formation of the cosmic web. As gravity pulls matter together to form the great filaments and clusters, it necessarily leaves behind these vast, underdense regions. But the properties of these voids, their size, their shape, their degree of emptiness are sensitive probes of the underlying cosmology. For instance, the nature of dark energy has a direct impact on the evolution of voids. A universe with a strong, repulsive dark energy will have voids that grow larger and emptier over time, as the cosmic acceleration pushes matter out of them more efficiently. By studying the statistics of voids at different cosmic epochs, astronomers can place constraints on the properties of dark energy, providing a powerful, independent check on the measurements from supernovae and the CMB. Webb is a powerful tool for this kind of void cosmology. Its sensitivity allows it to detect the faint, isolated dwarf galaxies that live within the voids, providing the crucial tracers needed to map their structure and evolution. But voids are not just tracers of dark energy, they may also be laboratories for testing our understanding of gravity. Some modified gravity theories, proposed as alternatives to dark energy, predict that the law of gravity should be different in low-density environments. In these theories, the gravitational force can be screened in high-density regions like our solar system, which is why we do not see any deviation from general relativity locally. But in the low-density environment of a cosmic void, this screening mechanism would be less effective, and deviations from Einstein's gravity might become apparent. By studying the motions of galaxies on the edges of voids and the weak gravitational lensing of background light by the sparse matter within them, we can test these modified gravity theories with unprecedented precision. The voids, in this sense, become the perfect place to look for a breakdown of our standard laws of physics. Finally, the voids are the best place to search for the subtle, large-scale signatures of the early universe. The faint temperature fluctuations in the cosmic microwave background are thought to be the seeds of all structure, but they have been processed and modified over billions of years of gravitational evolution. The voids, however, have evolved much less than the dense regions. They are, in a sense, a more direct, less processed window into the primordial universe. By studying the subtle patterns in the distribution of the few galaxies that do exist within voids, we may be able to detect the faint, non-Gaussian signatures predicted by some models of cosmic inflation, or even the aforementioned cosmic bruise that could signal a collision with another universe. The great cosmic voids are no longer the boring, empty spaces on the cosmic map. They are a new frontier, rich with information, a place where the secrets of dark energy, gravity, and the very beginning of the universe may be waiting to be discovered. They are a testament to the fact that in cosmology, as in so much of science, there is often as much to be learned from the absence of things as there is from their presence. The dynamic, energetic nature of the quantum vacuum, as described by zero-point energy, provides a new and powerful lens through which to view the very origin of the universe, offering a potential path to answering the ultimate cosmological question: why is there something rather than nothing? The traditional Big Bang model, while remarkably successful, has a fundamental limitation. It describes the evolution of the universe from a hot, dense state, but it cannot explain the origin of that state itself. The initial singularity is a point where the laws of physics break down, a moment of creation that lies outside the realm of scientific explanation. But the physics of the quantum vacuum allows for a different kind of beginning, a beginning that is not a violation of physical law, but a consequence of it. This is the concept of the universe from nothing, a concept that is often misunderstood. The nothing in this context is not the absolute, philosophical nothingness of non-existence. It is the quantum vacuum, a state devoid of matter and radiation, but rich with potential energy and subject to quantum fluctuations. In this picture, our universe could have been born from a spontaneous quantum tunneling event, just as a quantum particle can tunnel through an energy barrier that it classically could not overcome. The universe itself could have tunneled into existence from a state of nothing to a state of something. This idea was most famously developed by physicists like Alexander Vilenkin and Stephen Hawking in his no-boundary proposal. In this model, the universe did not have a beginning in time, because time itself was created in the tunneling event. The question, what came before the Big Bang, becomes meaningless. Just as it is meaningless to ask what is north of the North Pole, the universe did not arise in time, it arose with time. It is a self-contained, self-creating system, born from the inherent quantum restlessness of the void. This is a profoundly beautiful and self-consistent picture. It removes the need for a supernatural creator or a first cause that lies outside of science. The universe, in this view, is the ultimate free lunch. The total energy of the universe is thought to be exactly zero. The positive energy of matter and radiation is perfectly balanced by the negative gravitational potential energy. Since the creation of a system with zero total energy does not violate the law of conservation of energy, the universe can, in principle, pop into existence from the vacuum without any external cause. The zero-point energy of the vacuum is the crucial ingredient that makes this possible. It is the energetic froth from which a zero-energy universe can spontaneously nucleate. This concept also leads naturally to the idea of a multiverse. If our universe can be created by a quantum fluctuation, there is no reason to think it was a unique event. The quantum vacuum is a fertile ground, and universes may be constantly bubbling into existence, each with its own set of physical laws and constants, determined by the specifics of the tunneling event. This provides an elegant, if unprovable, solution to the fine-tuning problem. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves on a planet that is hospitable to life. It is a selection effect. We could not have evolved to ask the question in any of the other, far more numerous, inhospitable universes. The origin of the universe is perhaps the deepest and most profound question that science can address. And while we may never have a definitive, final answer, the physics of zero-point energy has, for the first time, provided us with a plausible scientific framework for understanding how a universe like ours could come to be. It suggests that existence is not a strange and improbable exception, but perhaps the natural, and even inevitable, consequence of the laws of quantum mechanics playing out on the canvas of the void. Something exists because nothing, in the quantum sense, is fundamentally unstable. The creative, energetic, and foundational nature of the quantum vacuum, as described by the concept of zero-point energy, represents one of the most significant and revolutionary shifts in our understanding of reality since the birth of modern science. It is a concept that has taken us from a view of a static, passive, and empty space to a vision of a dynamic, creative, and endlessly energetic quantum sea. This is not just a change in a scientific model, it is a change in our fundamental relationship with the cosmos. We have learned that the solid world we perceive with our senses is a fleeting though emergent illusion, a temporary ripple on the surface of a much deeper but invisible reality. The particles that make up our bodies are not solid, immutable things, but localized vibrations of fields that extend throughout the entire universe. We are, in the most literal sense, woven from the fabric of the void. The forces that govern our world, from the light that allows us to see to the gravity that holds us to the earth, are mediated by the constant, fleeting dance of virtual particles born from the vacuum's energy. The very stability of the atoms that make us up is a delicate equilibrium with the zero-point fluctuations of the surrounding space. The grand architecture of the cosmos, the vast web of galaxies and voids, is a macroscopic fossil of the quantum turbulence of the early universe. The fate of our universe, its journey into an accelerating and perhaps eternal expansion, is being driven by the mysterious, repulsive pressure of the void itself, and the very origin of our reality. The event we call the Big Bang may have been a spontaneous quantum leap from the potential rich nothingness of the vacuum into the manifest existence we now inhabit. This is a worldview that is both profoundly humbling and deeply empowering. It is humbling because it reveals the severe limitations of our own perception and the vastness of our ignorance. 95% of the universe is made of dark matter and dark energy, mysterious entities whose nature we do not yet understand, but which are likely tied to the properties of the vacuum. Our entire existence is a fragile 5% exception in a vast, dark, and invisible cosmos. But it is also empowering because it is a testament to the incredible power of the human mind. Through the abstract language of mathematics and the rigorous process of scientific inquiry, we have been able to deduce the existence of this hidden reality, to measure its effects, and to begin to understand its profound implications. We have built tools, like the James Webb Space Telescope, that allow us to peer into the void and listen to its secrets. The quest to understand zero-point energy is a journey to the very heart of reality. It is a quest that connects the smallest scales with the largest, the beginning of time with its end, and the most abstract theories of physics with the most tangible questions of our own existence. It is a journey that is far from over. The great puzzles, like the cosmological constant problem and the nature of dark energy, remain unsolved. But in grappling with these puzzles, we are pushing the boundaries of human knowledge and expanding our vision of what is possible. The silent, invisible energy of the void is the ultimate scientific frontier, a frontier that promises to yield new discoveries, new technologies, and a new, more profound understanding of our place in the cosmic symphony. The universe is stranger, more beautiful, and more deeply interconnected than we ever dreamed, and the key to its deepest secrets may lie where we least expected it, in the perfect, potent, and creative power of its own emptiness.
Imagine standing at the edge of an abyss, a place of such profound emptiness that it seems to contain nothing at all. No light, no sound, no matter, not even the familiar framework of space and time. It is from this perfect void, from this conceptual nothingness, that everything that has ever existed and everything that will ever exist is thought to have exploded into being. Have you ever stood under a clear night sky, looked up at the scattered diamonds of distant stars, and felt the weight of that question? Why is there something when there could have been nothing at all? How is it possible that from this sheer, featureless emptiness, the entire tapestry of the cosmos, the galaxies, the stars, the planets, and eventually, the very consciousness that is asking this question was born. These are not idle philosophical musings. They are the central, driving questions of modern cosmology, and they lead us to a truth that is far stranger and more profound than any of our ancient myths. At the deepest, most fundamental level of reality, in the bizarre and beautiful realm of quantum mechanics, we have discovered that true emptiness does not exist. What we perceive as the void is, in fact, a turbulent, seething ocean of energy and potential, a place where something is constantly happening. It is a cosmic womb, a generative silence, a nothing that contains the seeds of everything. For millennia, human cultures have grappled with the concept of the void, attempting to capture its essence through myth, philosophy, and art. The ancient Greeks spoke of chaos, the formless, primordial abyss from which the first gods and the ordered cosmos emerged. In the rich tapestry of Hindu thought, we find the concept of shunyata, an emptiness that is not a nihilistic void, but a state of pure, unmanifest potential, a dynamic emptiness that is the source of all phenomena. The Tao Te Ching, one of the foundational texts of Taoism, begins with a meditation on the Wu, the nameless, formless void that is, paradoxically, the mother of the 10,000 things, the entirety of the manifest world. It is a remarkable testament to the pair of human intuition that these ancient contemplative traditions arrived at a vision of emptiness that resonates so deeply with the discoveries of 21st century physics. Our most advanced scientific theories, expressed in the rigorous language of mathematics, are now telling us a story that our ancestors seemed to know in their bones, that the void is not an absence, but a presence, not an end, but a beginning. Quantum mechanics, that strange and wonderful pillar of modern science, reveals that even in a perfect vacuum, a space cooled to absolute zero and shielded from all external influences, there is an incessant, irreducible quantum jiggle. This is the world of quantum fluctuations, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. This is not a theoretical fantasy. It is a direct consequence of one of the most fundamental principles of nature, Werner Heisenberg's uncertainty principle. Formulated in 1927, this principle states that there is an irreducible trade-off in our knowledge of certain pairs of properties of a quantum system. The more accurately you know a particle's position, the less accurately you can know its momentum, and vice versa. This fundamental uncertainty extends to energy and time. For a very short period of time, the energy of a system can be uncertain, allowing for these spontaneous, fleeting creations of matter and antimatter from the nothingness of the vacuum. This means that at the most fundamental level, there is no such thing as a truly empty or static space. Every point in the cosmos is permeated by a web of quantum fields, one for each type of fundamental particle. These fields are never completely at rest. They are always vibrating, always fluctuating, even in their lowest energy state. This irreducible minimum energy of the vacuum is known as zero-point energy. It is the baseline hum of the universe, the silent, ever-present music of the void. And this is not just a mathematical abstraction. The physical effects of these virtual particles and their zero-point energy can be measured. The Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and later confirmed experimentally, shows that two uncharged parallel metal plates placed very close together in a vacuum will be pushed together by an invisible force. This force is not gravity, nor electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain wavelengths, while the space outside the plates can accommodate all wavelengths. This creates a pressure differential, a net force pushing the plates together. The void itself can exert a physical force. It is a stunning, tangible demonstration that what we call emptiness is, in fact, a dynamic, energetic, and powerful medium. The creative potential of this quantum vacuum is not limited to the fleeting dance of virtual particles. It may be the very source of our entire universe. The theory of cosmic inflation, one of the cornerstones of modern cosmology, proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated, exponential expansion. The driving force behind this inflation is thought to have been the energy of a quantum field, known as the inflaton field, trapped in a high-energy, false vacuum state. As this field relaxed to its true lower-energy state, it released its stored energy, flooding the nascent universe with the matter and radiation we see today. In this picture, the universe is a kind of macroscopic quantum fluctuation, a bubble of reality that was inflated to cosmic proportions by the energy of the void. This idea leads to an even more mind-boggling possibility: the quantum foam, first envisioned by the physicist John Wheeler. This is the idea that at the smallest possible scales of distance, the so-called Planck length, an unimaginably small 10 to the power of minus 35 meters, the very fabric of space-time is not smooth and continuous, but a chaotic, turbulent foam of microscopic black holes and wormholes, constantly being created and annihilated by quantum fluctuations. At this fundamental level, our familiar notions of space and time break down. This is the realm of quantum gravity, the yet-to-be-discovered theory that will unify Einstein's general relativity with quantum mechanics. In this foamy, quantum reality, a sufficiently large fluctuation could, in principle, give rise to a new, expanding universe. Our cosmos could be a single, fortunate bubble that emerged from this infinite, eternal sea of quantum potential. This is the scientific version of a universe from nothing, a concept explored by physicist Lawrence Krauss. The nothing in this context is not an absolute philosophical void, but the rich, dynamic, and endlessly creative quantum vacuum. This completely inverts our classical understanding of reality. We no longer see the void as a passive, empty stage upon which the cosmic drama unfolds. We see the void itself as the primary actor, the generative source, the mother of all that is. The emptiness between the stars is not an absence. It is the presence of an infinite potential, a potential that, some 13.8 billion years ago, blossomed into the vast, complex, and beautiful universe we call home. And so, as you lie in the quiet of the night, as your consciousness begins to drift into the silent, inner space of sleep, you are, in a sense, returning to this primordial state. You are entering your own personal quantum vacuum, a space of pure potential, a space where new thoughts, new dreams, and new realities can be born from the creative silence of your own being. In the early 1980s, the standard Big Bang model, while remarkably successful in describing the evolution of the universe from a hot, dense state, was facing a series of deep, conceptual puzzles. It was like having a perfectly working car, but with no idea how the engine was built or why it had started in the first place. Then, on a cold December night in 1979, a young American physicist named Alan Guth, poring over his equations, had what he later called a spectacular realization. He had stumbled upon the cosmic ignition key. The theory he conceived that night The theory of cosmic inflation would not just solve the lingering puzzles of the Big Bang, it would fundamentally reshape our understanding of the first infinitesimal moments of creation, and it would do so by unleashing the immense creative power of the quantum vacuum. The story that inflation tells is a dramatic one. It proposes that in the very first flicker of time, between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe underwent a period of astonishing, hyper-accelerated, exponential expansion. It was a cosmic growth spurt of truly epic proportions. During this fleeting, almost timeless instant, the size of the universe increased by a factor of at least 10 to the power of 26. A number so large it is difficult to represent with analogies. It is like taking an object smaller than a single proton and stretching it to the size of a grapefruit in a time far shorter than it takes light to cross that same proton. This is not just an expansion in space. It is an expansion of space itself, a stretching of the very fabric of reality at a rate that completely dwarfs the speed of light. The engine that powered this explosive growth, according to inflationary theory, was the energy of a quantum field, dubbed the inflaton field, which was momentarily trapped in a high-energy, unstable state known as a false vacuum. Imagine a ball perched precariously in a small divot at the very peak of a vast, steep hill. It possesses a huge amount of potential energy, and it is in a state of metastable equilibrium. A tiny, quantum jiggle is all it would take to send it cascading down the hill, releasing its stored potential energy as the kinetic energy of motion. The false vacuum of the early universe was like this ball at the top of the hill. It was a state of incredibly high and uniform energy density, and this energy had a peculiar and powerful property. It exerted a strong, negative pressure, which, according to Einstein's theory of general relativity, creates a powerful gravitational repulsion. It was this anti-gravity of the false vacuum that drove the exponential, inflationary expansion. Eventually, this false vacuum state decayed, like the ball rolling down the hill, into the true, lower energy vacuum state of our current universe. This process, called reheating, was a cataclysmic event. The immense energy that had been stored in the inflaton field was released, flooding the now vast, empty universe with a hot, dense, and uniform soup of fundamental particles and radiation. This is the starting point of the standard hot Big Bang model. Inflation, in this sense, is not an alternative to the Big Bang. It is a prequel, a brilliant and necessary prologue that sets the stage and explains the seemingly miraculous initial conditions from which the rest of cosmic history unfolded. The true elegance of inflationary theory lies not just in its dramatic narrative, but in its remarkable ability to solve the deep, conceptual puzzles that had plagued the standard Big Bang model. One of the most profound of these was the horizon problem. When we observe the cosmic microwave background, CMB, the faint, relic radiation from the infant universe, we find that it has an almost perfectly uniform temperature in all directions, to an accuracy of about 1 part in 100,000. This is a profound mystery. In the standard Big Bang model without inflation, regions of the sky that are on opposite horizons today were never in causal contact with each other. They were too far apart for light, or any other signal, to have traveled between them in the time since the beginning of the universe. So, how could they have possibly reached the same temperature? It is as if you walked into a vast, cavernous room and found that the temperature at every single point was identical to within a tiny fraction of a degree, without any heating or cooling system to have ever been turned on. Inflation provides a beautifully simple solution. Before the period of exponential expansion, The region of space that would eventually become our entire observable universe was an incredibly tiny, subatomic patch. It was so small that it was in perfect causal contact with itself. There was plenty of time for all parts of this patch to interact, to exchange energy, and to reach a state of thermal equilibrium, a state of uniform temperature. Inflation then took this tiny, smooth patch and stretched it to astronomical proportions in the blink of an eye. The uniformity was preserved, locked into the expanding fabric of space, creating the smooth, isotropic universe we see today. The second major puzzle solved by inflation is the flatness problem. According to general relativity, the geometry of space-time is determined by its total density of matter and energy. If this density is above a certain critical value, the universe will be closed, like the surface of a sphere, and will eventually collapse. If it is below the critical value, the universe will be open, like the surface of a saddle, and will expand forever. The flat universe of Euclidean geometry is a special knife-edge case, corresponding to a density that is exactly equal to the critical density, and our observations tell us that our universe is astonishingly exquisitely flat. For this to be the case, the initial density of the universe at the time of the Big Bang would have had to be fine-tuned to a degree of precision that is almost beyond comprehension, about 1 part in 10 to the power of 60. This seems like an absurdly improbable coincidence. Inflation solves this problem in a natural and elegant way. Any initial curvature that the universe may have had, whether positive or negative, would have been stretched out and flattened by the immense exponential expansion, in the same way that inflating a small, wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to an observer on it. Inflation drives the geometry of the universe so close to perfect flatness that it is, for all practical purposes, indistinguishable from it. But inflation does more than just solve old problems. It makes a remarkable and testable prediction. The theory states that the tiny, unavoidable quantum fluctuations in the inflaton field itself during the period of inflation would not have been smoothed out. Instead, they would have been stretched to macroscopic and even astronomical scales. These stretched-in-time quantum fluctuations would have become the seeds of cosmic structure, the tiny variations in density that, over billions of years, would grow under the influence of gravity to become all the galaxies, the clusters of galaxies, and the vast cosmic web that we see today. The specific statistical properties of these primordial fluctuations, they're near, but not perfect, scale invariance. They are a unique fingerprint of inflation, and they have been confirmed with stunning precision by our detailed maps of the cosmic microwave background. We are, in the most literal and profound sense, the children of quantum fluctuations. Our entire cosmic home, with all its grandeur and complexity, is a macroscopic fossil of the inherent uncertainty of the primordial quantum void. A void that was momentarily supercharged with an incredible inflationary energy. The theory of inflation, in its more modern and sophisticated forms, has led to a concept that is even more profound and mind-altering than the Big Bang itself. The idea of eternal inflation and the multiverse. The Russian-American cosmologist Andrei Linde, one of the key architects of modern inflationary theory, realized that the process of inflation, once started, may be very difficult to stop. In his model of chaotic inflation, the inflaton field is not a single uniform entity, but a field that has different random values in different regions of the primordial universe. In some regions, the field will quickly roll down its potential hill. Inflation will end, and a bubble universe like ours will be born in a hot Big Bang. But in other regions, quantum fluctuations can kick the field up the hill, causing inflation to continue, and even to become a self-reproducing, eternal process. In this scenario, the end of inflation in our region was just a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate and constantly spawning new bubble universes. The Big Bang was not a singular, unique event in the history of time. It is a common, ongoing process in the vast, eternal landscape of the multiverse. This is a vision of reality that is almost impossible to fully comprehend. Our entire observable universe, with its hundreds of billions of galaxies, is just one bubble in an infinite, bubbling foam of other universes. And these other universes may not be like our own. The decay of the inflaton field in each bubble could lead to different vacuum states, resulting in different fundamental particles, different forces of nature, different physical laws. There could be universes with 2 dimensions of space, or 10. Universes where gravity is a repulsive force, or where the speed of light is different. Most of these universes would be sterile, bizarre, and inhospitable wastelands, incapable of supporting any form of complexity or life. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle to be explained. It becomes a simple selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves living on a planet with liquid water and a breathable atmosphere we could not exist to ask the question in any of the other, far more numerous, inhospitable environments. The multiverse, in this sense, provides a scientific, albeit untestable, explanation for the anthropic principle. The idea of eternal inflation and the multiverse is on the cutting edge of theoretical physics, and it is by no means universally accepted. Critics point out that it is, by its very nature, unobservable, and therefore may not be a truly scientific theory, but its proponents argue that it is a natural and almost unavoidable consequence of combining our best theories of cosmology and quantum field theory, and there may be ways to search for indirect, circumstantial evidence. If our bubble universe had, in its distant past, collided with another bubble, it might have left a bruise on our cosmos, a specific circular pattern of temperature fluctuations in the cosmic microwave background. The search for such a cosmic scar is an active, if long-shot, area of research. Whether the multiverse is a physical reality or a beautiful mathematical dream, the theory of inflation has fundamentally and irrevocably changed our view of our own origins. It has taken the Big Bang from a mysterious, unexplained singularity and placed it within a larger, dynamic, and potentially eternal cosmic context. It has shown us how the grand, macroscopic structure of our universe can be born from the subtle, microscopic quantum fluctuations of the void. And it has opened our minds to the breathtaking possibility that our entire cosmos is just a single, fleeting note in an infinite and eternal cosmic symphony. The concept of the Big Bang itself, the central event in our cosmic story, is one that is often shrouded in misconception. The popular image is that of a gigantic firework, a singular explosion happening at a specific point in a pre-existing, empty space. But this picture is fundamentally wrong. The Big Bang was not an explosion in space. It was an explosion of space. It was not an event that happened at a particular location. It was an event that happened everywhere at once. To grasp this counterintuitive idea, the analogy of an expanding balloon is helpful. If you imagine our three-dimensional space as the two-dimensional surface of a balloon, and you draw a number of dots on this surface to represent galaxies, then as you inflate the balloon, you will see that every dot is moving away from every other dot. An observer on any given dot would see all the other dots receding from them, and the further away a dot is, the faster it would appear to be moving away. There is no center to this expansion on the surface of the balloon. The expansion is happening everywhere. The fabric of the balloon itself is stretching. In the same way, the expansion of the universe is a stretching of the fabric of space-time. Every point in our current universe, including the point where you are right now, was part of that initial, infinitely hot and dense state. The Big Bang happened right here and everywhere else. This is a direct consequence of Einstein's general theory of relativity, which describes space and time not as a static, absolute background, but as a dynamic, physical entity that can be bent, warped, and stretched by the presence of matter and energy. The Big Bang, then, is not a theory of the origin of the universe from nothing. It is a theory of the evolution of the universe from a very hot, dense, and rapidly expanding initial state. It does not, in its standard form, address the question of what caused the Big Bang, or what, if anything, for it. Those are questions that lie beyond the domain of the theory. In the realm of quantum gravity and the speculative cosmologies we have discussed, the story that the Big Bang does tell is the story of the first 14 billion years of our universe's life. A story of cooling, of expansion, and of the gradual emergence of complexity from a state of primordial simplicity. In the first fractions of a second, the universe was an unimaginably hot and dense soup of fundamental particles, quarks, leptons, and the force-carrying bosons, a state known as a quark-gluon plasma. As the universe expanded and cooled, this plasma froze out. After about 1 microsecond, the quarks bound together to form the protons and neutrons that make up the nuclei of atoms. For the next few minutes, in a process known as Big Bang nucleosynthesis, these protons and neutrons fuse together to form the nuclei of the lightest elements, mostly hydrogen and helium. With trace amounts of lithium, the universe was still a hot, dense, and opaque plasma. The temperature was so high that electrons were not bound to the atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, preventing them from traveling any significant distance. The universe was dark, not because there was no light, but because the light was trapped. This period lasted for about 380,000 years. Then, as the universe continued to expand and cool, it reached a critical temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination. Suddenly, the fog lifted. The universe became transparent to light. The photons that were present at that time were now free to travel unimpeded through space, and they have been traveling ever since. Their wavelengths stretched by the subsequent expansion of the universe from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe, a beautiful uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent, a fossil that carries with it a wealth of information about the conditions of the early cosmos. The story of the Big Bang is a story of transformation, a story of how, from a state of almost perfect uniformity and simplicity, all the rich and complex structures we see today, the stars, the galaxies, the planets, and ourselves, were gradually born. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is our story. As our journey through the cosmos brings us closer to the present day, we encounter the universe's most profound and perplexing mystery, the existence of dark energy. This is not a subtle theoretical curiosity. It is the dominant component of our universe, making up roughly 68% of its total energy density. It is the invisible, silent force that is shaping the ultimate destiny of our cosmos. And we have almost no idea what it is. The discovery of dark energy in 1998 was a complete surprise. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at different times in its history. A Type Ia supernova is the thermonuclear explosion of a white dwarf star, and it always has the same intrinsic brightness, making it a perfect cosmic yardstick. The teams expected to find that the expansion of the universe was slowing down, as the mutual gravitational attraction of all the matter in the cosmos should be acting as a brake. To their astonishment, they found the exact opposite. The distant supernovae were dimmer than expected, which meant they were further away than they should have been if the expansion was slowing down. The expansion of the universe is accelerating. This groundbreaking discovery, which earned its leaders the 2011 Nobel Prize in Physics, implied the existence of a new, previously unknown form of energy with a strange and powerful property, a strong negative pressure that acts as a form of cosmic anti-gravity, pushing space-time apart. This is what we call dark energy. The simplest and most natural candidate for dark energy is the energy of the quantum vacuum itself. The zero-point energy we discussed earlier, in the context of Einstein's general relativity, a constant vacuum energy density would manifest as a cosmological constant, a term that Einstein himself had introduced into his equations in 1917, only to later retract it as his biggest blunder when Edwin Hubble discovered the universe was expanding. In a beautiful historical irony, modern cosmology has resurrected Einstein's blunder and made it the centerpiece of our standard cosmological model. A universe dominated by a cosmological constant has a strange and counterintuitive property. As space expands, the density of matter and radiation decreases as they are spread out over a larger volume, but the density of vacuum energy remains constant. This means that as the universe gets bigger, the total amount of dark energy increases. It is as if new energy is being created from the expanding space itself. In the early universe, when the density of matter and radiation was very high, the effects of dark energy were negligible. But as the universe expanded and thinned out, dark energy gradually became the dominant component. It took over from gravity as the primary driver of cosmic evolution about 5 billion years ago, and it has been accelerating the expansion ever since. The problem, as we have seen, is the vacuum catastrophe. The theoretical value of the vacuum energy calculated from quantum field theory is an absurd 120 orders of magnitude larger than the observed value of dark energy. This colossal discrepancy has led many physicists to believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence, that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps our understanding of gravity is wrong. Maybe general relativity needs to be modified on cosmological scales. These modified gravity theories attempt to explain the accelerated expansion without invoking any new form of energy. They propose that gravity itself becomes repulsive on very large distances. Distinguishing between these different possibilities is one of the primary goals of modern cosmology. Observatories like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the distribution of galaxies and the history of cosmic expansion with unprecedented precision, which will allow us to measure the properties of dark energy and to test whether it has changed over time. The nature of dark energy is not just a question for physicists. It is a question that touches on the ultimate fate of our universe. A universe dominated by a constant dark energy is destined for a big freeze. A universe dominated by a phantom energy that grows stronger over time is destined for a big rip. And a universe where dark energy could one day decay or change its sign could be destined for a big crunch. We live in a universe whose destiny is being written by an invisible, mysterious, and powerful force. A force whose true nature remains one of the greatest and most profound challenges in all of science. The empty space that surrounds us is not empty at all. It is a dynamic, energetic, and powerful entity, a cosmic protagonist whose story we are only just beginning to understand. The idea that our universe might not be the only one, that it could be part of a vast, perhaps infinite, multiverse, is a concept that has migrated from the realms of science fiction and philosophy into the heart of modern theoretical physics. It is a breathtaking and humbling idea, one that, if true, would represent the final and most profound step in the Copernican revolution, the long historical process of de-centering humanity from a privileged position in the cosmos. The concept of the multiverse is not a single, coherent theory, but rather a consequence of several of our most ambitious and successful physical theories. We have already encountered one of its most compelling sources, the theory of eternal cosmic inflation. In this picture, our universe is just one bubble that formed when a small patch of an eternally inflating meta-universe decayed into a lower energy state. Other bubbles are constantly forming, each potentially with different physical laws, constants, and even different numbers of dimensions. This creates a vast, Level 2 multiverse of disconnected parallel realities. Another powerful argument for the multiverse comes from the many worlds interpretation of quantum mechanics. As we discussed, this interpretation, first proposed by Hugh Everett, solves the measurement problem by positing that the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple branches, with each branch corresponding to one of the possible outcomes. This creates a Level 3 multiverse, a constantly branching tree of parallel realities. In this multiverse, there are an infinite number of yous, each living out the consequences of a different quantum outcome. There is a version of you who is reading this, and a version of you who decided to go for a walk instead. Every possibility is realized somewhere in this vast quantum multiverse. A third, and more straightforward, type of multiverse is the Level 1 multiverse. This is simply the idea that our observable universe, the region of space from which light has had time to reach us since the Big Bang, is just a small patch of a much larger and possibly infinite universe. If space is infinite, then in that infinite volume, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far beyond our cosmic horizon, there is another galaxy, another solar system, another Earth, and another you. An identical copy living out an identical life. And there are an infinite number of such copies. This is a staggering and deeply unsettling thought, one that challenges our sense of individuality and uniqueness. Finally, there is the most abstract and philosophical type of multiverse, the Level 4, or mathematical universe, proposed by physicist Max Tegmark. This is the idea that physical reality is, at its core, a mathematical structure. And since all consistent mathematical structures exist in a timeless, Platonic sense, then all possible mathematical structures exist as physical realities. Our universe is just one, particularly complex, mathematical structure, one that happens to have the right properties to allow for the emergence of self-aware substructures, like us, who can contemplate the mathematical nature of their own existence. The multiverse, in all its forms, provides a powerful, if controversial, framework for addressing the fine-tuning problem. The fact that the physical constants of our universe seem to be so exquisitely tuned to allow for the existence of life is no longer a miracle that requires a supernatural explanation. It is a simple selection effect. We find ourselves in a universe that is hospitable to life because it is the only kind of universe we could find ourselves in. We are the survivors of a cosmic lottery of unimaginable proportions. The primary criticism of all multiverse theories is that they are, by their very nature, untestable. We can never travel to another bubble universe or communicate with a parallel branch of the quantum wave function. This has led some to argue that the multiverse is not a scientific theory, but a metaphysical one. But its proponents argue that the theories from which the multiverse arises, like inflation and quantum mechanics, are themselves highly testable. If these theories continue to pass every experimental test we throw at them, then we may be forced to take their more bizarre consequences, like the multiverse, seriously. And there may be indirect, circumstantial ways to search for evidence. The cosmic bruise from a collision with another bubble universe is one such possibility. The search for a variation in the fundamental constants of nature across the sky is another, whether the multiverse is a physical reality or not. The very fact that it is a serious topic of discussion among many of the world's leading physicists is a testament to how far our cosmic horizons have expanded. It is a concept that forces us to confront the true scale of reality, to question our most basic assumptions about our own uniqueness, and to embrace a vision of the cosmos that is infinitely richer, stranger, and more magnificent than we ever dared to imagine. As we gaze out into the cosmos, our vision is fundamentally limited. The night sky appears as a vast, dark dome, but this is an illusion. We are not looking out at a static, three-dimensional space. We are looking back in time. The light from the moon takes a little over a second to reach us, so we see it as it was a second ago. The light from the sun takes 8 minutes. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years. And the light from the Andromeda Galaxy, our closest major galactic neighbor, has been traveling for 2.5 million years. When we look at the most distant galaxies visible in the James Webb Space Telescope, we are seeing them as they were over 13 billion years ago. When the universe was just a toddler, this intimate connection between distance and time defines our cosmic horizon. Because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, there is a fundamental limit to how far we can see. The boundary of our observable universe is not a physical wall, but a temporal one. It is the distance from which light has had just enough time to reach us since the Big Bang. We can never, even in principle, see what lies beyond this horizon. The universe may be infinite, but our view of it is finite. The situation is made even more profound by the accelerating expansion of the universe. Not only is there a horizon that limits our view of the past, but there is also an event horizon that limits our view of the future, because space itself is expanding, and this expansion is accelerating. Distant galaxies are receding from us at ever-increasing speeds. There is a critical distance beyond which galaxies are receding from us faster than the speed of light. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this event horizon will never be able to reach us. They will be easily disconnected from our future. They will, in a sense, disappear from our universe. The night sky of the far future will be a profoundly lonely place. As more and more galaxies recede beyond our event horizon, the cosmic landscape will become increasingly empty. Eventually, only the members of our own, gravitationally bound local group of galaxies will remain visible. A future civilization, looking up at the sky, might conclude that they live in a single island universe, forever unaware of the vast cosmic ocean that we are privileged to still be able to see. This concept of an event horizon, a one-way membrane that separates the observable from the unobservable, is most famously associated with black holes. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. Its event horizon is the point of no return. Any object or any information that crosses this boundary is lost to the outside universe forever. In the 1970s, Stephen Hawking revolutionized our understanding of black holes by showing that they are not completely black. Due to quantum effects at the event horizon, the constant creation and annihilation of virtual particle pairs from the quantum vacuum black holes should slowly emit a faint thermal radiation. This Hawking radiation causes the black hole to lose mass and, over immense timescales, to eventually evaporate completely. This brilliant theoretical discovery, which elegantly weaves together the principles of general relativity, quantum mechanics, and thermodynamics, also gave rise to one of the deepest paradoxes in modern physics, the black hole information paradox. According to the fundamental principles of quantum mechanics, information can never be destroyed. The total amount of information in a closed system must always be conserved. But if you throw an encyclopedia, with all its rich and complex information, into a black hole, that information seems to be lost forever behind the event horizon, and when the black hole evaporates, the Hawking radiation it emits appears to be purely thermal and random, containing no memory of the information that fell in. So, where does the information go? Is it truly destroyed? In violation of one of the most sacred principles of physics? Or does it somehow escape, subtly encoded in the quantum correlations of the outgoing radiation? This paradox has been a major driver of research in theoretical physics for decades, and its resolution is thought to be a key step towards a full theory of quantum gravity. Recent theoretical work has suggested that the information is not lost, but is preserved on the event horizon itself, a concept related to the holographic principle, which posits that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. The existence of horizons, both cosmological and black hole, is a profound and humbling feature of our universe. It tells us that there are fundamental, built-in limits to our knowledge. There are parts of the cosmos and aspects of nature that may forever lie beyond the reach of our direct observation, but they are also a powerful spur to our theoretical imagination, forcing us to devise new and creative ways to understand the realities that are hidden from our view. They are a reminder that the universe is not a transparent, open book, but a deep and multi-layered mystery. A mystery whose most profound secrets are often hidden right at the very edge of what we can see. The grand narrative of our cosmos, as told by the standard Big Bang model, is a linear one. It is a story with a definite beginning, a long period of evolution, and a potential final end. But is this the only possible story? Could the universe be a more timeless, more cyclical entity, an eternal dance of creation and destruction, with no absolute beginning or end? This idea of a cyclic universe, of an endless dance of creation and destruction, is one of the oldest and most enduring ideas in human thought. It is found in the kalpas of Hindu cosmology, vast time cycles of cosmic creation, maintenance, and dissolution. It is present in the philosophy of the ancient Stoics, with their idea of a great year at the end of which the universe is consumed by fire and then reborn. And it is an idea that has been given a new scientific life in some of the most advanced and speculative theories of modern cosmology. The simplest version of a cyclic universe is one that ends in a big crunch. If the total density of matter and energy in the universe is high enough, then the mutual gravitational attraction will eventually overcome the cosmic expansion, causing the universe to slow down, stop, and then begin to contract, eventually collapsing back into a hot, dense singularity, a mirror image of the Big Bang. This singularity could then bounce, triggering a new Big Bang and a new cycle of expansion. This bouncing universe model was popular for a time, but it fell out of favor with the discovery of dark energy and the accelerating expansion of the universe, which seems to rule out an eventual collapse. It also suffers from a serious theoretical problem, the second law of thermodynamics. With each cycle, the entropy, or disorder, of the universe should increase. This means that each cycle should be longer and more diffuse than the last. And it is hard to see how a universe that has existed for an infinite number of cycles in the past could still be in the relatively ordered state we see today. But in the early 21st century, a new and more sophisticated version of the cyclic model was proposed by physicists Paul Steinhardt and Neil Turok. Their ekpyrotic or cyclic model is based on the ideas of string theory and extra dimensions. In this picture, our universe is a three-dimensional brane, or membrane, floating in a higher dimensional space, or bulk. There is another parallel brane nearby. In this picture, the Big Bang is not the beginning of time, but is the result of a gentle periodic collision between our brane and this other brane. Each collision releases a tremendous amount of energy, which is converted into the hot, dense matter and radiation of a new cosmic cycle. After the collision, the branes move apart, and our universe expands and cools, just as in the standard Big Bang model. But the story does not end there. A form of dark energy, in this model a potential energy between the branes, eventually causes them to slow down and begin to move back towards each other, drawn together by a spring-like force. This leads, after a period of slow contraction, to another gentle collision, another Big Bang, and the beginning of a new cycle. Each of these cycles could last for 1 trillion years or more, an almost unimaginable timescale from a human perspective, but just a single beat in the eternal rhythm of the cosmos. This cyclic model has several elegant features. It avoids the initial singularity of the standard Big Bang model, as the branes themselves never reach infinite density. It can also explain the observed smoothness and flatness of our universe without the need for a period of cosmic inflation. The smoothness is a result of the long period of slow contraction before the last bang, which had plenty of time to smooth out any irregularities. It also provides a natural explanation for dark energy as the force that drives the cycles. The model also offers a potential solution to the entropy problem. The vast expansion that occurs during each cycle so dilutes the entropy that it becomes negligible, effectively resetting the cosmic clock. The cyclic model is still a minority view in the cosmological community, and it faces a number of significant theoretical challenges, particularly in describing the physics of the brane collision itself, a process that requires a full, and as yet unknown, theory of quantum gravity. But it remains one of the most compelling and well-developed alternatives to the standard inflationary Big Bang paradigm. It offers a vision of the cosmos that is not a one-off event, but an eternal, self-renewing, and resilient process. It is a vision that connects the frontiers of theoretical physics with some of the oldest and most profound intuitions of the human spirit. It is a reminder that the story of the universe may not have a beginning or an end, but may be a beautiful and endlessly repeating cosmic poem. The apparent, exquisite fine-tuning of the fundamental constants of nature to allow for the existence of life is one of the most puzzling and philosophically charged aspects of modern cosmology. It is as if we have walked into a cosmic casino and found that all the roulette wheels have been preset to the winning numbers. The strength of gravity, the mass of the electron, the value of the cosmological constant. If any of these numbers were even slightly different, the universe would be a sterile and lifeless place. This has led to the formulation of the anthropic principle, a controversial but powerful idea that attempts to explain this cosmic coincidence by appealing to our own existence as observers. The weak anthropic principle is a relatively straightforward and almost tautological statement. It simply says that the conditions we observe in the universe must be compatible with our own existence. We are here, we are conscious, we are made of carbon, and therefore, the universe must have properties that allow for the formation of carbon-based, conscious observers. This is a form of selection bias. We are filtering the possible universes we could observe by the very fact of our own being. It is like a fish wondering why the world is so full of water. It is a valid, but not particularly deep explanation. The strong anthropic principle. However, he makes a much bolder and more metaphysical claim. It suggests that the universe is, in some sense, compelled to have properties that allow for the emergence of life and consciousness at some point in its history. This can be interpreted in several ways, from the theological, a divine designer, to the teleological, a cosmic purpose. The anthropic principle, in its weak form, finds a natural and scientific home in the context of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of other universes, each with its own randomly assigned set of physical constants, then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a universe that is hospitable to life. It is a statistical inevitability. We are simply living in one of the rare, life-friendly bubbles in the vast, cosmic landscape of the multiverse. This is a powerful and elegant explanation, but it comes at a price. It requires us to accept the existence of a potentially infinite number of unobservable universes, a concept that many find to be a violation of the principle of Occam's razor, which states that we should not multiply entities beyond necessity. The debate between the multiverse anthropic explanation and the search for a more fundamental, unified theory that would uniquely determine the values of the constants is one of the central intellectual battles in modern theoretical physics. Is the universe the way it is because it is the only way it could be, its properties fixed by a deep and elegant mathematical necessity? Or is it the way it is because it is just one of a vast ensemble of possibilities, and we are simply the lucky winners of a cosmic lottery? There are also alternative and more speculative approaches to the fine-tuning problem. The physicist Lee Smolin has proposed a model of cosmological natural selection. In this picture, universes can reproduce by creating new, baby universes inside the black holes that form within them. When a new universe is born, its fundamental constants can be slightly randomly mutated from those of its parent. Over many generations of universes, a process akin to biological natural selection would favor those universes whose constants are fitter, meaning they produce more black holes and therefore more offspring. Smolin argues that the same constants that lead to a high rate of black hole production, which requires a universe with long-lived stars, abundant carbon, and complex chemistry, are also the constants that are conducive to life. In this view, our life-friendly universe is not a random fluke, but the product of a long, cosmic, evolutionary history. The fine-tuning problem is a beautiful example of how a precise scientific observation can lead us to the deepest and most profound philosophical questions. It forces us to confront our own place in the cosmos, to ask whether our existence is a cosmic accident or a cosmic necessity, a random roll of the dice, or the fulfillment of a deep, underlying purpose. And as you lie on the threshold of sleep, you can ponder the fact that your own conscious awareness is the very thing that makes this question possible, a single, precious point of view from which the universe can begin to contemplate its own mysterious and perhaps meaningful existence. The quest to understand the universe in its grandest sweep is a quest for unification. It is the search for a single, elegant, and comprehensive theory that can explain all the disparate phenomena of nature, from the dance of subatomic particles to the evolution of the cosmos, within a single coherent mathematical framework. This was Einstein's dream, the goal he pursued for the last 30 years of an otherwise spectacularly successful scientific life, and it remains the holy grail of modern theoretical physics. The current state of our knowledge is a tale of two theories, general relativity and the standard model of particle physics. General relativity is Einstein's magnificent theory of gravity, a theory that describes gravity not as a force, but as the curvature of a dynamic, four-dimensional spacetime. It is a theory of the large scale of planets, stars, galaxies, and the expanding universe. The standard model, on the other hand, is our theory of the small scale. It is a quantum field theory that describes the other three fundamental forces of nature: the electromagnetic force, the weak nuclear force, and the strong nuclear force, and all the known elementary particles, like quarks, leptons, and the Higgs boson. Both of these theories have been tested to an incredible degree of precision and have passed every experimental test with flying colors. They are, without a doubt, the two most successful scientific theories in the history of humanity. But they are fundamentally incompatible. They are written in different mathematical languages and are based on different physical principles. General relativity is a classical, deterministic theory of a smooth, continuous spacetime. The standard model is a quantum, probabilistic theory that plays out on a fixed, static spacetime background. This incompatibility becomes a critical problem in certain extreme regimes of nature, where both gravity and quantum effects are important. In the fiery crucible of the Big Bang, or in the infinitely dense singularity at the center of a black hole, our two great theories break down and give nonsensical, infinite answers. To understand these ultimate frontiers of reality, we need a new theory, a theory of quantum gravity that can seamlessly weave together the principles of general relativity and quantum mechanics. The search for this theory is the primary occupation of a large portion of the theoretical physics community today. One of the leading candidates, as we have seen, is string theory. In this ambitious framework, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different vibrational modes of these strings correspond to the different particles we see in nature. One particular vibration corresponds to the graviton, a hypothetical quantum particle of gravity. In this way, string theory naturally incorporates gravity into a quantum framework, but it does so at a price. The mathematical consistency of the theory requires the existence of extra, hidden dimensions of space, typically 6 or 7 of them, which are curled up into a tiny complex Calabi-Yau manifold at every point in our familiar three-dimensional space. The precise shape and size of these extra dimensions determine the properties of the strings, and therefore, the physical laws of our universe. String theory is a framework of breathtaking mathematical beauty and elegance, and it has the potential to unify all the forces and particles of nature. But it has, so far, failed to make any unique, testable predictions that would allow us to confirm or falsify it. The alternative approach is loop quantum gravity, Instead of starting with particles and trying to quantize gravity, loop quantum gravity starts with space-time itself and tries to quantize it directly. In this theory, space is not a continuous background, but is made of discrete quantum atoms of space, each with a volume of about the Planck length cubed. These atoms are connected together in a network called a spin network, and the evolution of this network in time creates a spin foam. Space-time, in this picture, is not a smooth fabric, but a dynamic, evolving quantum graph. Loop. Quantum gravity is a beautiful and conceptually radical theory, and it has had some notable successes, such as providing a calculation of the entropy of a black hole. But like string theory, it is still a work in progress, and it has struggled to show how the familiar smooth space-time of our macroscopic world can emerge from this underlying, discrete quantum structure, and how the standard model of particle physics can be incorporated into its framework. The search for a unified theory of everything is one of the most difficult and ambitious endeavors in the history of science. It is a search that pushes the limits of our mathematics, our technology, and our very imagination. But it is a search that is driven by a deep and powerful faith, a faith that the universe, at its most fundamental level, is simple, elegant, and comprehensible. A faith that the two great warring narratives of modern physics can and must one day be united into a single, beautiful, and complete story. The cosmological constant problem, the vacuum catastrophe, is more than just a numerical discrepancy. It is a deep, conceptual chasm that lies at the very heart of modern physics, a stark and humbling reminder of the vastness of our own ignorance. The problem, in its essence, is the collision of our two most successful physical theories, general relativity and quantum field theory, in the seemingly simple context of empty space. Quantum field theory tells us that the vacuum is not empty, but is filled with a seething sea of zero-point energy, the sum of the ground state energies of all the quantum fields that pervade the universe. When we try to calculate the energy density of this vacuum, using the principles of quantum mechanics, we get a number that is staggeringly large. General relativity, on the other hand, tells us that any form of energy is a source of gravity. It curves space-time. If the vacuum energy were truly as large as the quantum calculation suggests, its gravitational effect would be catastrophic. It would curve space-time so violently that the universe would have expanded into a diffuse, empty void in the first fraction of a second of its existence. There would be no stars, no galaxies, no planets, no us. But this is not what we observe. We observe a universe that is expanding and even accelerating, but at a rate that is incredibly, exquisitely slow compared to the theoretical prediction. The observed value of the cosmological constant, the energy density of the vacuum that is driving the cosmic acceleration, is about 120 orders of magnitude smaller than the naive theoretical calculation. This is a discrepancy of a 1 followed by 120 zeros. It is, without a doubt, the worst theoretical prediction in the entire history of physics. It is as if you tried to calculate the weight of a single grain of sand, and your answer was the weight of the entire Earth. Something is fundamentally and profoundly wrong with our understanding. The problem is not that we have two competing theories. It is that our two best theories, when combined, give a result that is spectacularly, absurdly wrong. There have been many proposed solutions to this profound puzzle, but none has gained widespread acceptance. The idea of supersymmetry, a hypothetical symmetry between the two fundamental classes of particles, bosons and fermions, offers a partial solution. In a perfectly supersymmetric world, the vacuum energy contributions from the bosons and the fermions would exactly cancel each other out, leading to a vacuum energy of zero. This is an elegant mathematical solution, The problem is that our world is not perfectly supersymmetric. If it were, we would have already discovered the superpartners of all the known particles. And we have not. Supersymmetry, if it exists, must be a broken symmetry, meaning the superpartners are much heavier than their standard model counterparts. A broken supersymmetry would no longer lead to a perfect cancellation. And while it could reduce the predicted value of the vacuum energy, it still requires an incredible amount of fine-tuning to get it down to the observed tiny value. Another, more philosophical, approach is to appeal to the anthropic principle in the context of a multiverse. If there are an infinite number of bubble universes, each with a different randomly determined value of the cosmological constant, then it is no surprise that we find ourselves in one of the rare universes where this value is small and positive, allowing for the formation of galaxies and life. In most other universes, the vacuum energy would be so large that they would either instantly collapse or expand into nothingness. This is a logically consistent explanation, but it is deeply unsatisfying to many physicists, as it abandons the hope of a fundamental, physical explanation for one of the most important parameters of our universe. Other, more radical, proposals involve modifying the laws of gravity or quantum mechanics. Perhaps the vacuum energy does not gravitate in the same way as normal matter and energy. Perhaps our understanding of how to calculate the vacuum energy in quantum field theory is fundamentally flawed. The cosmological constant problem is a sign that we are missing a major piece of the puzzle. It is a crack in the foundations of modern physics, a crack through which the light of a new, deeper understanding may one day shine. Its resolution will likely require a full theory of quantum gravity, a theory that can consistently combine the principles of general relativity and quantum mechanics. And it is a problem that should instill in us a deep sense of intellectual humility. It is a reminder that even our most successful and well-tested theories are still just provisional approximations of a much deeper and far more mysterious reality. The empty space that surrounds us, the seemingly simple nothingness of the void, contains a secret that is so profound that it has, so far, defeated the collective intelligence of the most brilliant minds in the history of science. It is the ultimate puzzle, waiting patiently in the silence for a new Einstein to come along and solve it. The unidirectional flow of time, the arrow of time, is one of the most fundamental and yet most mysterious aspects of our experience. We are born, we live, we die. We remember the past, but not the future. Cause always precedes effect. This seems so obvious, so deeply ingrained in the fabric of our reality, that we rarely stop to question it. But when we look at the fundamental laws of physics, this arrow of time is nowhere to be found. The laws of Newtonian mechanics, of electromagnetism, of relativity, and even of quantum mechanics are all, with one minor exception related to the weak nuclear force, time symmetrics. They work just as well for a movie played forwards as for a movie played backwards. If you were to film a collision between two billiard balls and play the movie in reverse, it would still look like a perfectly valid physical interaction. So, if the fundamental laws of nature do not have a preferred direction of time, why does the macroscopic world of our experience so clearly do? The answer, as we have seen, lies in the second law of thermodynamics, the law of increasing entropy. The universe as a whole, and any isolated system within it, tends to evolve from a state of low entropy high order to a state of high entropy high disorder. A whole egg is a low entropy state. A scrambled egg is a high entropy state. There are vastly more ways for the molecules of an egg to be arranged in a scrambled configuration than in an ordered whole configuration. So the system, when left to its own devices, will naturally evolve towards the state of higher probability, the state of higher entropy. This gives time its thermodynamic arrow, but this just pushes the question back a step. Why was the universe in such an incredibly low entropy, highly ordered state to begin with? If the early universe, at the time of the Big Bang, had started in a state of thermal equilibrium, a state of maximum entropy, then nothing would have ever happened. There would be no arrow of time, no evolution, no complexity, no life. The fact that we live in a universe with a strong arrow of time is a direct consequence of the fact that it started in a state of extraordinary and seemingly improbable order. This is the ultimate cosmological puzzle, the past hypothesis. Why the low entropy beginning? The Austrian physicist Ludwig Boltzmann, in the 19th century, proposed a statistical explanation. Perhaps our observable universe is just a temporary, random fluctuation into a state of low entropy within a much larger and much older meta-universe that is, for the most part, in a state of thermal equilibrium, a state of heat death. We just happen to live in a rare, ordered bubble. The problem with this idea, as was later pointed out, is that it leads to the bizarre Boltzmann's brain paradox. It would be statistically far more likely for a single, conscious brain with a full set of false memories of a past that never happened to fluctuate into existence for a brief moment, than for an entire, ordered universe like ours to do so. This makes the statistical fluctuation explanation seem deeply problematic. Modern cosmology has offered other, more sophisticated, potential solutions. The theory of cosmic inflation, by stretching a tiny, smooth patch of the early universe to astronomical scales, can help to explain the homogeneity of our starting point. But it does not fully solve the problem of its low entropy. The British physicist Roger Penrose has proposed a bold and elegant solution in his theory of conformal cyclic cosmology. He argues that the far future of our universe, after an infinite amount of time has passed and all matter has decayed into a sea of massless photons, becomes geometrically indistinguishable from the hot, dense, low entropy state of a Big Bang for a new eon of the cosmos. In this picture, the universe goes through an infinite sequence of cycles, with the heat death of one eon becoming the low entropy Big Bang of the next. The arrow of time is reset with each new cycle. The quest to understand the origin of the arrow of time is a quest to understand the very origin of order, of structure, and of complexity in our universe. It is a question that connects the deepest principles of thermodynamics, cosmology, and quantum mechanics. And it is a question that is intimately tied to our own subjective experience of being. We are creatures of memory and anticipation, beings who are fundamentally oriented in time. Our consciousness is a process that is constantly weaving the raw data of the present into a coherent story that connects a remembered past with an imagined future. We are, in a very real sense, embodiments of the arrow of time. And as you lie on the threshold of sleep, as your own personal sense of time begins to dissolve into the timeless, dreamlike state of the unconscious, you can ponder this deep and beautiful mystery, the simple, familiar, and yet profoundly unexplained fact that time flows, that the universe evolves, that there is a difference between yesterday and tomorrow, may be the greatest and most wonderful miracle of all. The universe, in its grandest conception, may be far more complex and multi-layered than our familiar 3 dimensions of space and 1 of time would suggest. Some of our most ambitious and elegant physical theories, like string theory, require the existence of extra, hidden dimensions to be mathematically consistent. This is a mind-bending idea, but it is one that has a long and respectable history in theoretical physics, The idea is that these extra dimensions are not like the large, extended dimensions we are familiar with. They are compactified, curled up into a tiny, complex geometrical shape at every single point in our space. Imagine a garden hose. From a great distance, it looks like a one-dimensional line, but as you get closer, you see that it has a second, circular dimension that was previously hidden from view. In the same way, the extra dimensions of string theory are thought to be curled up on a scale so small, the Planck length, that they are completely inaccessible to our current experiments. The precise shape and size of these extra dimensions, the geometry of this Calabi-Yau manifold, is not just a mathematical curiosity, it is the key to everything. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different ways these strings can vibrate correspond to the different fundamental particles we see in nature. An electron is a string vibrating in one pattern. A photon is a string vibrating in another. And the geometry of the extra dimensions determines which vibrations are possible, and what the properties of the resulting particles, their mass, their charge, their spin will be. The laws of physics are, in this sense, a consequence of geometry. This is a breathtakingly beautiful and ambitious idea. It has the potential to unify all the forces and particles of nature into a single coherent framework, a theory of everything. The problem is that string theory does not predict a unique geometry for the extra dimensions. In fact, it allows for a vast, and possibly infinite, number of possible Calabi-Yau manifolds, a landscape of at least 10 to the power of 500 different possible vacuum states, each corresponding to a different set of physical laws. This has led to a deep split in the theoretical physics community. Some see this landscape problem as a fatal flaw in the theory, a sign that it is not a truly predictive theory, but a postdictive one that can be tweaked to fit any observation. Others, however, see it as the theory's greatest triumph. When combined with the idea of eternal inflation, the string theory landscape provides a physical basis for the multiverse. Each of the 10 to the power of 500 possible vacua could be realized in a different bubble universe, creating a vast ensemble of different physical realities. The anthropic principle then becomes a natural and powerful tool for explaining why we find ourselves in a universe with our specific set of physical laws. But the idea of extra dimensions has led to other equally fascinating cosmological models. The brain cosmology scenario, which we have touched upon, posits that our entire three-dimensional universe is a brain, a membrane floating in a higher dimensional bulk space. The forces, ephemeras, and particles of the standard model are confined to our brain, like drawings on a sheet of paper, while gravity, the geometry of space-time itself, is free to propagate in the bulk. This could explain why gravity is so much weaker than the other forces. Its influence is being diluted by the extra dimensions. This scenario opens up a host of new and exciting possibilities. There could be other parallel brains floating in the bulk, other universes separated from us by a tiny distance in a fourth spatial dimension. The Big Bang could have been the result of a collision between our brain and another. Dark matter could be the gravitational influence of matter on a nearby parallel brain. Dark energy could be the result of a force between the brains. These are speculative ideas, to be sure, and they are far from being experimentally verified, but they are not just idle fantasies. They are the logical consequences of taking our best physical theories seriously and following them to their ultimate conclusions. They are a testament to the power of the human imagination, guided by the rigor of mathematics, to conceive of realities that are far beyond the limits of our direct experience, and they serve as a profound reminder that the world we see, the familiar three dimensions of our everyday life, may just be a shadow, a projection of a much richer, much deeper, and much more complex, multidimensional reality. As you close your eyes and your consciousness begins to detach from the familiar coordinates of your bedroom, you can let your mind drift into this higher dimensional space, a space where our entire universe is just a fragile membrane, a single note in a symphony played out in a reality whose true dimensionality we are only just beginning to imagine. The age-old dialogue between science and religion, between the empirical quest to understand the how of the universe and the spiritual quest to understand the why, has been one of the most fraught, and also most fruitful, in the history of human thought. The story of creation, the origin of the cosmos, has always been at the heart of this dialogue. For millennia, humanity has turned to its religious and mythological traditions to answer the ultimate questions of existence. The creation myths of the world, from the Genesis story of a six-day creation by an omnipotent God, to the Hindu concept of a cyclical universe born from the dream of Vishnu, are not scientific theories. They are profound, symbolic narratives that seek to provide a sense of meaning, of purpose, and of our place within a sacred cosmic order. Modern scientific cosmology, with its story of a 14-billion-year-old universe born from a Big Bang and governed by impersonal physical laws, can seem, at first glance, to be a direct and irreconcilable challenge to these ancient stories. This has led to a spectrum of responses. At one extreme, we find a position of conflict. Young Earth creationists, who insist on a literal interpretation of the Genesis story, reject the overwhelming scientific evidence for an old universe and for biological evolution. At the other extreme, we find a form of scientific materialism or scientism, which argues that science is the only valid path to knowledge, and that religious beliefs are simply outdated, pre-scientific superstitions that should be abandoned. But between these two warring poles, there lies a vast and fertile ground for a more nuanced and constructive dialogue. Many scientists and theologians today advocate for a position of independence or non-overlapping magisteria noma, a term coined by the late paleontologist Stephen Jay Gould. In this view, science and religion are two distinct and legitimate domains of human inquiry that address different kinds of questions. Science deals with the empirical realm, with the how of the natural world. Religion deals with the realm of ultimate meaning, of morality, of purpose, the why of human existence. They are two different languages, two different ways of knowing, and they are not in inherent conflict because they are not trying to answer the same questions. A third position is one of dialogue or integration. In this view, science and religion are not just independent, but can actually enrich and inform each other. Theologians can learn from the discoveries of science, which can provide a more accurate and awe-inspiring picture of the created world, a picture that can deepen and refine their theological understanding. The discovery of a vast, ancient, and evolving universe, for example, can lead to a more mature and less anthropocentric understanding of the creator. Scientists, in turn, can benefit from the deep existential questions and the ethical frameworks that religion provides. Science can tell us how to clone a human being, but it cannot tell us whether we should. The great questions of meaning, of value, of purpose, which are often the initial motivation for a scientific career, are not, in themselves, scientific questions. The Catholic Church, for example, has had a long and complex relationship with science, but its modern position is one of dialogue and integration. The Big Bang Theory was first proposed by a Catholic priest, Georges Lemaitre, and the Church today officially accepts the scientific accounts of the Big Bang and evolution as being compatible with Christian faith, seeing them as the means by which God's creative purpose unfolds in the world. In the Islamic tradition, there is a rich history of scientific inquiry during the Islamic Golden Age. And many contemporary Muslim thinkers are engaged in a vibrant dialogue between the Quranic worldview and the findings of modern science. And in the Eastern traditions, like Buddhism and Hinduism, the relationship is often even less fraught. The cyclical, vast, and non-theistic cosmologies of these traditions often have a more natural resonance with the worldview of modern physics than the linear, creation ex nihilo stories of the Abrahamic faiths. The dialogue between science and religion is not about finding a single, unified answer. It is about fostering a sense of intellectual humility, a recognition of the limits of our own ways of knowing, and an appreciation for the different and equally valuable paths that humanity has taken in its long and enduring quest to understand its place in the grand, mysterious, and sacred tapestry of the cosmos. The ultimate question, the one that lies beneath all of our scientific and philosophical inquiries, is the question posed by the philosopher Gottfried Wilhelm Leibniz in the 18th century. Why is there something rather than nothing? This is a question that seems to teeter on the very edge of reason. Nothing, in an absolute sense, is almost impossible for the human mind to conceive of. And yet, it seems, on the face of it, to be the simpler, more natural state. Existence, with all its complexity, its laws, its beings, seems to demand an explanation. Why did the universe go to all the trouble of existing modern physics? As we have seen, has offered a scientific gloss on this question. The universe from nothing scenario in quantum cosmology suggests that our universe could have spontaneously tunneled into existence from a pre-existing quantum vacuum. A nothing that is not a true void, but a state of pure potential. This is a powerful and elegant idea, but it does not fully answer Leibniz's question. It simply pushes it back a step. It explains how our universe could have arisen from the quantum vacuum, but it does not explain why there is a quantum vacuum, with its specific laws and properties, rather than an absolute, philosophical nothingness. To address this deeper question, some thinkers have turned to the realm of mathematics. The physicist Max Tegmark, in his mathematical universe hypothesis, has proposed a radical and breathtaking solution. The hypothesis states that physical reality is a mathematical structure, not just that it can be described by mathematics, but that its fundamental nature is mathematical. In this view, all possible, consistent mathematical structures have a real physical existence. Our universe is just one such structure, a particularly complex and self-aware one. If this is true, then the question, why this universe, is answered. It exists because it is mathematically possible. The universe exists for the same reason that 2 + 2 = 4, for the same reason that the Pythagorean theorem is true. It exists by logical necessity. This is a form of ultimate Platonism, the idea that the abstract world of mathematical forms is the true, fundamental reality. This hypothesis also provides a natural home for the multiverse. All the different possible mathematical structures correspond to different universes, with different physical laws, particles, and dimensions. The fine-tuning problem is solved, and the existence of our universe is no longer a surprise, but a necessity. This is a deeply compelling idea, but it is also highly controversial and, at present, unfalsifiable. It blurs the line between physics and metaphysics in a way that many find uncomfortable. It raises deep questions about the relationship between the abstract and the concrete, between the map and the territory. Another related approach is the idea of an ultimate principle of sufficient reason. Perhaps the universe exists because it is, in some deep, logical sense, the simplest or most elegant possible reality. Or perhaps, as the philosopher Robert Nozick speculated, the state of nothingness is inherently unstable. Perhaps nothingness contains within it a force that nothings itself, leading inevitably to the existence of something. These are ideas that are on the very frontier of human thought, where the languages of physics, mathematics, and philosophy begin to merge. They are the modern, secular equivalent of the theological quest for God as the uncaused cause, or the necessary being. Whether any of these approaches will ever lead to a final, satisfying answer is an open question. It is possible that the question, "Why is there something rather than nothing?" is a question that is, in principle, unanswerable from within the system of existence. It may be a question that is designed not to be solved, but to be held, to be contemplated, to be a source of endless wonder and humility. And as you lie in the quiet of the night, on the verge of sleep, you can feel the weight and the beauty of this ultimate mystery. The very fact that you exist, that you are a conscious, questioning being in a universe of something, is a miracle that is either the result of a random, inexplicable chance, or the expression of a deep, beautiful, and inescapable logical necessity. The choice between these two perspectives may be the most fundamental choice of all. Our long and winding journey through the origin of the universe, from the quantum foam to the multiverse, from the Big Bang to the arrow of time, has been a journey through the landscape of modern science. But this entire landscape, with all its theories, its data, its equations, is ultimately perceived, conceived, and understood through the lens of one of the most mysterious and profound phenomena in the entire cosmos, our own: human consciousness. We have spoken of the observer in quantum mechanics, but what is this observer? Is it a simple mechanical measuring device? Or is there something special, something fundamental, about the role of a conscious mind in the unfolding of reality? This is a question that has haunted the fringes of physics for a century, and it is one that is now beginning to move closer to the center of scientific inquiry. The hard problem of consciousness. The question of how a physical system like the brain can give rise to the rich, subjective, and qualitative world of our inner experience remains one of the greatest unsolved challenges in all of science. The classical, materialistic view, which sees the brain as a complex biological computer and consciousness as an emergent property of its information processing, failed to provide a convincing explanation for the raw feel of experience. This has led some thinkers to propose that consciousness may not be an emergent property of complexity, but a fundamental property of the universe, on par with space, time, and mass. This is the essence of panpsychism, the ancient idea that mind, in some rudimentary form, is a ubiquitous feature of reality. In this view, an electron does not just have a physical aspect, but also a mental aspect, a tiny, primitive flicker of proto-consciousness. As matter becomes more complex and organized, as in a living cell or a human brain, these tiny flickers of mind can combine and integrate, giving rise to the rich, self-aware consciousness that we experience. This is a radical idea, but it is one that is gaining a new respectability as a potential solution to the hard problem. It avoids the seemingly impossible task of trying to get consciousness to emerge from purely non-conscious ingredients. Instead, it suggests that consciousness has been there all along, woven into the very fabric of the cosmos. The theory of orchestrated objective reduction, OR, proposed by Roger Penrose and Stuart A. Hameroff, offers a specific physical mechanism for how this might work. It suggests that consciousness is a quantum computational process occurring in the microtubules of our brain's neurons, a process that is intimately linked to the fundamental Planck scale geometry of space-time. In this model, each moment of conscious awareness is a quantum collapse event, a moment where the superpositional potential of the brain's quantum state is resolved into a definite classical experience. This is a bold and speculative theory, but it is one that makes testable predictions. And it is a beautiful example of how the mysteries of the quantum world and the mysteries of the mind might be two sides of the same deep coin. Another, related, idea is that of the universe as a vast information processing system. The physicist John Wheeler's famous dictum, "It from bit," suggests that the fundamental reality is not matter or energy, but information, and that the physical world is a manifestation of this underlying informational reality. In this view, consciousness is not just a processor of information. It is, in some sense, the very medium through which information acquires meaning and becomes reality. This is the essence of Wheeler's participatory anthropic principle. The idea that the universe, through the emergence of conscious observers, brings itself into being. We are not just spectators of the cosmic drama. We are participants, co-creators of the story. The questions we ask, the observations we make, the meaning we find, these are not just reflections of a pre-existing reality. They are an integral part of its ongoing creation. As you lie on the threshold of sleep, as your own individual consciousness begins to dissolve and merge into the vast, mysterious realm of the unconscious, you can ponder this profound and beautiful possibility. The very consciousness that is listening to these words, that is contemplating the origin of the universe, may not be just a fleeting, accidental byproduct of a random, chemical process on a small, insignificant planet. It may be a fundamental, necessary, and creative aspect of the cosmos itself, a tiny, precious window through which the universe comes to know, to feel, and to wonder at its own magnificent existence. Our exploration of the cosmos, both in its vast outer reaches and its deep inner nature, inevitably brings us to the edge of our own knowledge, to the horizon of what we can see and what we can know. We have peered back in time to the faint, ancient light of the first galaxies. We have conceived of realities beyond our own observable universe, of multiverses and extra dimensions. We have even dared to ask what might have come before the beginning of time itself. But in this quest, we are always confronted with our own fundamental limitations. The cosmic particle horizon, the boundary of our observable universe, is a real and seemingly insurmountable barrier. We can never directly see into the regions of space that lie beyond it. The cosmic event horizon, created by the accelerating expansion of the universe, is an even more final boundary, a one-way membrane that will forever hide the most distant parts of the cosmos from our view. The Planck scale, the realm of quantum gravity, represents a fundamental limit to the resolution with which we can probe the fabric of space-time, and the very nature of scientific inquiry, with its reliance on testable, falsifiable hypotheses, may mean that some of the grandest and most compelling ideas of modern cosmology, like the multiverse, will forever remain in the realm of metaphysics. But these limitations are not a cause for despair. On the contrary, they are a source of profound intellectual humility and a powerful spur to our creativity. The history of science is a history of pushing boundaries, of finding clever, indirect ways to probe the realities that lie beyond our direct grasp. We cannot see a black hole, but we can infer its presence from the dance of the stars that orbit it and from the gravitational waves it emits when it collides with another. We cannot see an exoplanet's surface, but we can deduce the composition of its atmosphere from the faint starlight that filters through it. In the same way, physicists are constantly devising new and ingenious ways to search for the indirect, circumstantial evidence of the realities that lie beyond our current horizons. They are searching for the cosmic bruises in the CMB that could signal a collision with another universe. They are looking for the subtle signatures of extra dimensions in the behavior of particles at the Large Hadron Collider. They are listening for the faint, primordial whisper of gravitational wheeze from the moment of inflation. This is a quest that requires patience, ingenuity, and a deep appreciation for the subtle art of scientific inference. It is a quest that acknowledges its own limits, but refuses to be bound by them. And this quest is not just about expanding our knowledge of the external world, it is also about expanding our understanding of ourselves. The realization that we live in a universe with fundamental horizons, that our knowledge will always be partial and incomplete, can be a powerful antidote to the arrogance and dogmatism that have so often plagued human history. It invites us to adopt a stance of openness, of curiosity, of wonder. It reminds us that the universe is not a problem to be solved, but a mystery to be lived. And as we stand on the shore of this vast, cosmic ocean of the unknown, we are not alone. We are part of a long, unbroken chain of human inquiry. A chain that stretches back to our most ancient ancestors who first looked up at the night sky and wondered. We are the inheritors of their questions and the custodians of their legacy. And as you surrender to the gentle, restorative mystery of sleep, you can feel a sense of connection to this great human adventure, the very consciousness that is about to drift into the timeless, boundaryless realm of dreams is the same consciousness that has dared to ask the biggest questions, to imagine the grandest possibilities, and to reach for the stars. The journey is far from over. The greatest discoveries, the most profound revelations, may still lie ahead, waiting patiently for us in the deep, silent, and beautiful darkness that lies just beyond the horizon of our current understanding. The golden age of cosmology in which we are now living is a testament to the power of human ingenuity and our insatiable desire to understand our place in the cosmos. With a new generation of powerful telescopes, gravitational wave detectors, and particle accelerators, we are poised to answer some of the longest-standing questions in science, and, in the process, to uncover new mysteries that we cannot yet even imagine. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared, is already revolutionizing our view of the early universe. In the coming years, it will continue to push our observational frontier ever closer to the Big Bang, searching for the light of the very first stars and galaxies. The cosmic dawn when the universe first lit up, it will provide us with detailed chemical fingerprints of the atmospheres of hundreds of exoplanets, searching for the telltale signs of life beyond Earth. It will peer into the dusty hearts of stellar nurseries and protoplanetary disks, giving us an unprecedented view of the birth of stars and worlds. On the ground, a new generation of massive 30-meter class optical telescopes, like the giant Magellan telescope and the 30-meter telescope, will provide a synergy with Webb, allowing for high-resolution follow-up observations of the most interesting objects it discovers. In the realm of radio astronomy, the Square Kilometer Array, a continent-spanning network of thousands of radio antennas, will map the distribution of neutral hydrogen in the early universe, providing a three-dimensional picture of the cosmic web and the epoch of reionization, the period when the light from the first stars and quasars ionized the neutral gas that filled the cosmos. The search for the nature of dark matter and dark energy will enter a new phase of precision, the Vera C. Rubin Observatory, with its vast 8.4-meter mirror and its 3.2 gigapixel camera, will survey the entire southern sky every few nights for a decade, creating the deepest and widest map of the universe ever made. Its data will allow us to trace the history of cosmic expansion with unprecedented accuracy, to map the distribution of dark matter through weak gravitational lensing on a vast scale, and to search for the fleeting signatures of transient events like supernovae and kilonovae. The Euclid Space Telescope will provide a complementary high-resolution view, mapping the shapes of billions of galaxies to to study the subtle distortions caused by dark matter and dark energy. The detection of gravitational waves has opened a completely new window onto the universe, a window that allows us to hear the cosmos, not just see it. The current network of LIGO, Virgo, and Kagra detectors will be upgraded to increase their sensitivity, allowing them to detect the faint ripples in space-time from more distant and more exotic cosmic cataclysms. And in the 2030s, the Laser Interferometer Space Antenna LISA, a constellation of 3 spacecraft flying in a triangular formation millions of kilometers apart, will take gravitational wave astronomy into space. LISA will be sensitive to the low-frequency gravitational waves emitted by the mergers of supermassive black holes in the centers of distant galaxies, and potentially to the faint stochastic background of gravitational waves from the very first moments of the Big Bang itself. This could provide a direct, unambiguous confirmation of cosmic inflation and a glimpse into the physics of the universe at energies far beyond the reach of any terrestrial particle accelerator. On the theoretical front, the quest for a theory of quantum gravity will continue, guided by the subtle clues provided by these new observations, and perhaps by the new computational power of quantum computers, which could one day allow us to simulate the complex dynamics of quantum spacetime directly. This is a moment of unprecedented opportunity in the history of science. We are living at a time when we have the tools, the theories, and the global collaborative spirit to address some of the deepest and most profound questions that humanity has ever asked. The journey is long, the challenges are immense, and the ultimate answers may forever lie just beyond our grasp. But the quest itself, the shared human endeavor to understand our cosmic home, is one of the noblest and most beautiful expressions of our species. It is a quest that connects us to our past, gives meaning to our present, and inspires our hopes for the future. And as you close your eyes and let the universe of your own mind unfold in the quiet theater of your dreams, you can feel a sense of participation in this grand human adventure. The consciousness that is about to journey into the mysterious inner cosmos of sleep is the same consciousness that is, at this very moment, reaching out to the stars, listening for the echoes of creation, and striving to read the silent, beautiful, and endlessly fascinating story of the universe. Good night, and may your dreams be as vast and as wonderful as the cosmos itself.